Close your eyes for a moment. I want you to imagine something extraordinary happening right now. Not tomorrow, not next week, but this very second. Approximately 70 million cosmic rays are passing through your body. Not around it, through it. From the crown of your head to the tips of your toes. High-energy particles born in the hearts of dying stars and accelerated to nearly the speed of light are streaking through your cells, your organs, your very DNA. And here's the truly mind-bending part. This has been happening continuously for your entire life, for your parents' lives, for the entire 4-billion-year history of life on Earth. We are, quite literally, living inside a cosmic storm, one so pervasive, so constant, that we've evolved to barely notice it. But what if I told you that this invisible bombardment may have been the architect of everything you are? That the thoughts in your brain, the shape of your body, the fact that you can stand upright and contemplate the cosmos, all of it might trace back to particles arriving from across the galaxy. This is the story of cosmic rays and human evolution. And it begins not with us, but with violence on a scale almost impossible to comprehend. Somewhere in the vast cosmic deep, perhaps 1,000 light-years away, perhaps 10,000, a massive star is dying. I'm talking about a star so enormous that if you placed it where our Sun sits, its surface would stretch past Jupiter. This giant has lived a violent life, fusing hydrogen into helium, then helium into carbon, then carbon into oxygen, nitrogen, silicon, all the way up the periodic table, creating heavier and heavier elements in a cascading nuclear furnace. But all things end. When the core finally begins fusing iron, the star's fate is sealed. Iron fusion consumes energy rather than releasing it, and in the span of seconds, not years, not days, but seconds, the core collapses catastrophically. What happens next is called a supernova explosion, and it's the most violent event in the known universe, short of a black hole. The collapse reverses almost instantaneously, and a shock wave tears through the star's outer layers, accelerating them to speeds of 30,000 kilometers per second. The explosion releases more energy than our Sun will emit in its entire 10-year lifetime, all in a few moments. And in that apocalyptic furnace, something remarkable occurs. The dying star becomes an enormous particle accelerator. Protons and heavier atomic nuclei, we call them cosmic rays, are caught in the shockwave's magnetic field and accelerated to tremendous speeds. Imagine a particle moving at 99.9999% the speed of light. That's cosmic rays. These particles are so energetic, so devastatingly powerful, that when a single cosmic ray slams into Earth's atmosphere, it can generate a cascading shower of secondary particles, billions of them, cascading down through the sky like a subatomic fireworks display.
What are cosmic rays really? Let me be precise about what we're dealing with here. Cosmic rays aren't actually rays, they're particles. About 87% of them are protons, the nuclei of hydrogen atoms. Another 12% are helium nuclei, alpha particles, and the remaining 1% consists of heavier elements, carbon, nitrogen, oxygen, iron, and even trace amounts of uranium and plutonium. These percentages reflect the composition of the universe itself, a cosmic fingerprint left by the processes that forged them. What makes cosmic rays so distinctive is their energy. Most particles we encounter in everyday life are relatively calm, moving at ordinary speeds. But cosmic rays are different. We measure their energy in units called electron volts, abbreviated EV. A single electron volt is minuscule. It takes 1.6 times 10 to the minus 19 joules of energy to move one electron through 1 volt of electrical potential. Most cosmic rays arriving at Earth carry energies of a few billion electron volts, or GeV. But the most extreme ones, the ultra-high energy cosmic rays, carry energies of 100 million billion electron volts or more. These super-rare particles have so much energy that when they collide with our atmosphere, they create secondary showers containing quintillions of particles. To put this in perspective, a baseball pitched at 100 miles per hour carries about 145 joules of energy. A single ultra-high energy cosmic ray carries as much energy as a baseball being thrown by a pitcher on the moon with enough force to reach Earth, all concentrated in a subatomic particle. So these cosmic rays are born in stellar explosions, but they don't arrive at Earth immediately. After their violent acceleration in a supernova shockwave, they begin an astonishing journey through interstellar space. Some travel in straight lines, but most encounter magnetic fields, vast invisible structures threading through the galaxy, and these fields bend their paths. A cosmic ray might spiral around these magnetic field lines for thousands or millions of years, gradually drifting through the galaxy, passing through clouds of gas, dodging planets, navigating the invisible architecture of the cosmos. Some cosmic rays originate from our own galaxy, the Milky Way. These are called galactic cosmic rays. But here's something that might surprise you. We also receive cosmic rays from beyond the Milky Way's boundaries. Cosmic rays arriving from beyond the Milky Way's boundaries are called extragalactic cosmic rays, and they originate in distant galaxies, some of them billions of light-years away. They carry the signatures of catastrophes happening across the entire observable universe. The cosmic flux, the number of cosmic rays hitting Earth per unit area per unit time, is highest near the poles and lowest near the equator. This variation holds the first clue to how Earth protects itself, something we'll explore in detail later. But the fundamental point is this: cosmic rays are everywhere. They're coming from all directions simultaneously, a constant rain of high-energy particles that had continued for billions of years.
Now here's where things get truly fascinating. When a cosmic ray, especially a high-energy one, hits Earth's upper atmosphere, it doesn't simply vanish. Instead, it collides with nitrogen or oxygen nuclei, and that collision is so violent that it shatters both particles into fragments. These fragments are themselves energetic particles that cascade downward, creating more collisions, generating more particles, in a chain reaction that physicists call an extensive air shower. Imagine a cosmic ray hitting the atmosphere at 100 kilometers altitude. Boom! It shatters a nitrogen nucleus. This creates several secondary particles, pions, muons, photons, each carrying a fraction of the original particle's energy. These secondary particles collide with other atmospheric molecules, creating more secondaries in a spreading cone that reaches the ground with millions of particles across an area many meters wide. This cascade happens incredibly fast, in nanoseconds, but it's fundamental to understanding how cosmic rays influence life on Earth. Because, here's the crucial point, it's these secondary particles, not the original cosmic rays, that reach us. At sea level, we're mostly exposed to muons, particles that are heavier cousins of electrons, and to photons, particles of light. The original cosmic ray protons were absorbed high in the atmosphere, but their offspring keep coming. The cosmic ray flux is actually quite predictable and has been measured with remarkable precision. At Earth's surface, we're hit by roughly 1 cosmic ray per square centimeter per minute. That might not sound like much, but remember that your body contains trillions of cells, and each cell contains a nucleus with a double helix of DNA. Over your lifetime, billions of cosmic rays will pass through your body. Most will pass through without interacting with anything, but some, a small fraction, will interact with a DNA molecule, with a water molecule in your cells, or with other biological structures. And when they do, things get interesting. Before life evolved on Earth, before the first microbes invented DNA, cosmic rays were already here, raining down on the infant planet. When Earth first coalesced from dust around a newborn sun 4.5 billion years ago, the planet was bombarded by solar wind and cosmic rays with virtually no atmospheric or magnetic protection. As an atmosphere began to accumulate and as Earth's core started generating a magnetic field, the cosmic ray flux reaching the surface decreased, but it never stopped. It's been a constant environmental pressure, like gravity or heat or the availability of water. And here's the profound realization. If something has been a constant environmental factor for billions of years, life doesn't just adapt to it. Life may actually evolve with it, shaped by it, enhanced by it. Evolutionary pressures aren't always negative. A source of mutations is also a source of variation, and variation is the raw material of natural selection. Imagine a war without weapons, without soldiers, without even sound. A war being fought in the realm of plasma and magnetic fields, invisible to human eyes, yet absolutely decisive in determining whether life can exist on Earth. This war has been raging for the entire 4.5 billion year history of our solar system, and on one side of this conflict stands our Sun. Most of us think of the Sun as a simple thing, a ball of burning gas that sits 93 million miles away, providing heat and light. That's not wrong, but it's profoundly incomplete. The Sun is far more than a passive furnace. It's an active combatant in an endless struggle against cosmic rays trying to reach Earth. It's a bodyguard, and understanding how our Sun protects us is essential to understanding how cosmic rays have shaped our evolution. Every second, the Sun releases an enormous stream of charged particles, mostly protons and electrons, flowing outward in all directions at speeds of roughly 400 to 700 kilometers per second. We call this the solar wind. It's not gentle, it's not a whisper, it's a continuous gale of plasma, ionized gas, being hurled away from the Sun's corona, its outer atmosphere, into interplanetary space. The mass involved is staggering. Every single second, the Sun loses about 1 million tons of material through the solar wind. Over a year, that's roughly 32 billion kilograms of matter ejected into space. Over 1 billion years, which is nothing on cosmic timescales, the Sun sheds a mass equivalent to Jupiter into the solar system. Yet the Sun is so enormous that this loss is barely noticeable. It's like a human losing a few skin cells per minute, significant over a lifetime, but negligible in the moment. But here's what matters for our story. This solar wind is charged. The protons and electrons flowing outward carry electrical charges, and moving electrical charges generate magnetic fields.
The Sun's rotating magnetic field gets wound up and stretched by the solar wind, creating an enormous spiral structure of magnetic field lines that extends all the way out to the edge of the solar system. We call this the interplanetary magnetic field, or IMF, and it's the invisible barrier that stands between Earth and the galactic cosmic rays trying to infiltrate our neighborhood.
The region of space dominated by the Sun's magnetic field and solar wind is called the heliosphere. Think of it as an enormous bubble surrounding the solar system, with the Sun at its center and the edge of this bubble located roughly 100 to 120 astronomical units from the Sun, well beyond the orbit of Neptune, in a region called the heliopause, where the solar wind's outward pressure finally equals the inward pressure of the interstellar medium. This bubble is everything. It's our shield. It's the invisible fortress protecting the inner planets from the raw cosmic radiation flooding through interstellar space. Without the heliosphere, cosmic ray exposure on Earth would be dramatically higher, perhaps by a factor of 2 or more. Life as we know it might not have had the chance to evolve. Now, here's something crucial. The heliosphere isn't constant. It fluctuates, it expands and contracts, its magnetic field strength varies, and these variations are determined by something called solar activity, which follows recognizable patterns. If you were to observe the Sun's surface over the course of several years, you'd notice something remarkable. The number of sunspots rises and falls in a regular, predictable rhythm. A sunspot is a region where the Sun's magnetic field is concentrated, thousands of times more powerful than Earth's magnetic field, and where convection is disrupted, making those regions appear darker and cooler than the surrounding photosphere. The number of sunspots increases and decreases in a cycle that averages about 11 years. This is called the solar cycle, or Schwab's cycle, named after the amateur astronomer Heinrich Schwab, who first documented it in 1844 by tracking sunspots over decades. At the solar minimum, sunspots are rare, sometimes absent for weeks. At the solar maximum, dozens or even hundreds of sunspots might be visible simultaneously. Then the cycle repeats. Why does this matter? Because sunspot activity is directly correlated with the strength of the Sun's magnetic field and the intensity of the solar wind. During solar maximum, the Sun's magnetic field is turbulent and strong, the solar wind is more vigorous, and the interplanetary magnetic field is more robust. This stronger IMF does a better job of deflecting incoming cosmic rays. During solar minimum, the Sun's magnetic field weakens, the solar wind becomes calmer, and the IMF relaxes its grip. Cosmic ray flux reaching Earth actually increases during solar minimum by something like 5% or 10%, depending on the cosmic ray's energy. This might seem like a small variation, but on evolutionary timescales, with generations of organisms exposed to this rhythm over millennia and millions of years, those variations accumulate. They create environmental pressures that organisms must adapt to. The process by which the Sun's magnetic field weakens or strengthens the cosmic ray flux reaching Earth is called solar modulation. It's a fascinating interplay of physics. Here's how it works. A cosmic ray traveling through the heliosphere encounters the Sun's magnetic field lines, which are frozen into the plasma of the solar wind, meaning the magnetic field lines move along with the plasma, wrapped around particles like an invisible rope. When a cosmic ray, also a charged particle, encounters one of these field lines, the magnetic field exerts a Lorentz force on it, bending its trajectory. Low-energy cosmic rays are bent most easily.
High-energy cosmic rays, carrying more momentum, are bent less. But essentially, the magnetic field acts like a sieve, filtering out many of the cosmic rays trying to reach the inner solar system. When the Sun's magnetic field is strong during solar maximum, this filtering effect is most pronounced. Fewer cosmic rays make it to Earth. When the Sun's magnetic field is weak during solar minimum, the filter becomes less effective, and more cosmic rays penetrate to Earth's vicinity. But here's where it gets even more interesting. The Sun's magnetic field doesn't just vary over 11 years. It also exhibits much longer-term variations. There are periods called grand minima, lasting decades or sometimes centuries, during which solar activity drops dramatically. The most famous example is the Maunder minimum, which lasted from approximately 1645 to 1715 and coincided with a period of particularly cold climate on Earth, part of what's called the Little Ice Age. During the Maunder minimum, sunspots virtually vanished. Astronomical records show almost none were observed during that entire 70-year period. The Sun, it seemed, had gone quiet. When the Sun goes quiet, cosmic rays flood in. During the Maunder minimum, cosmic ray flux at Earth increased substantially. Scientists have been able to document this by analyzing isotopes in ice cores and tree rings. Cosmic ray interactions with the upper atmosphere produce specific isotopes like carbon-14 and beryllium-10, and these get incorporated into ice and plant material. By measuring how much of these isotopes accumulated in ice from the Maunder minimum period, researchers found clear evidence of elevated cosmic ray activity.
Now, I want to pose a deeper question, one that leads directly to the central hypothesis of this entire report. What if Earth's solar system passes through regions of the galaxy where the cosmic ray background is naturally higher? The Milky Way is not a uniform disk of stars and gas. It contains spiral arms, regions of higher star density that spiral outward from the galactic center. Our Sun orbits the galactic center, taking about 230 million years to complete one full orbit. As it orbits, sometimes it passes through spiral arms, sometimes it doesn't. When Earth's solar system passes through a galactic spiral arm, it spends time in a region where supernova explosions are more frequent, where there are more cosmic ray sources, and where the background cosmic ray flux is higher. Estimates suggest that our solar system may pass through significant spiral arms every 100 to 150 million years, and each passage might last 5 to 10 million years. During these passages, Earth experiences a period of elevated cosmic ray exposure, a cosmic ray storm that lasts for millions of years. The Sun's heliosphere still provides protection, but the pressure on it increases. More cosmic rays get through. This is where the evolutionary implications become fascinating. Imagine a species existing during such a passage. Mutations would increase, the genetic variation in populations would expand. Some mutations would be harmful, yes, increased cancer rates and genetic damage, but others might provide advantages, creating variation that natural selection could act upon. Evolution does not occur at a constant rate. It can be accelerated by environmental pressures, and an increased cosmic ray flux is exactly such a pressure. Here's the paradox that makes the Sun's role so profound. The Sun is both our protection and our vulnerability. It shields us from cosmic rays, but its shield fluctuates. During periods of high solar activity, it provides maximum protection. During grand minima, the shield weakens. During galactic spiral arm passages, the baseline cosmic ray flux is higher, so even the Sun's best protection leaves us more exposed than during quieter cosmic times. Over the 4.5 billion years of Earth's history, our planet has experienced multiple spiral arm passages, multiple grand minima in solar activity, countless solar cycles, and long periods of relative calm. The cosmic ray exposure reaching Earth's surface has never been static. It's been a variable, fluctuating quantity, sometimes peaking high, sometimes dropping to baseline levels. And critically, and this is what we must keep in our minds as we move forward, these variations in cosmic ray exposure correspond to different periods in Earth's history. When cosmic rays were more abundant at Earth's surface, what was happening to life? Were evolutionary changes accelerating? Were new traits emerging? Were extinction events occurring?
The Sun's protection is real and essential. Without the heliosphere, without the interplanetary magnetic field, cosmic ray exposure at Earth would be perhaps 2 or 3 times higher. Life might have evolved, but it would have faced more constant damage, more mutations, more pressure. In that sense, the Sun has been a savior, enabling life to exist on a habitable world. But the Sun's shield is also dynamic, and that dynamism introduces variability into the environment. And variability in cosmic ray exposure, in radiation stress, in evolutionary pressure, is the driving force of evolution itself. Over millions of years, species that evolved under high cosmic ray stress might accumulate different mutations, develop different DNA repair mechanisms, or experience different selection pressures than species evolving under lower cosmic ray conditions. The Sun stands as Earth's bodyguard, but it's a bodyguard whose vigilance waxes and wanes, whose shield sometimes strengthens and sometimes weakens, creating a rhythm of environmental variation to which all life on Earth must adapt. In the next chapter, we'll descend from the scale of the solar system down to the scale of the planet itself. We'll discover that Earth has its own bodyguard, one even more intimate and perhaps even more crucial, the magnetosphere, a protective shield generated by Earth's own iron core. And like the Sun's shield, Earth's shield has its vulnerabilities, particularly a dramatic weakness that occurs once every few 100,000 years, a moment when Earth's magnetic field doesn't simply weaken, it completely reverses. When that happens, the cosmic ray flux reaching Earth's surface spikes temporarily, and for a brief moment in geological time, our planet stands almost naked before the cosmic rays.
If the Sun is humanity's cosmic bodyguard, then Earth itself is a fortress. Deep beneath your feet, beneath the soil, beneath the bedrock, beneath the mantle that churns with molten rock, there exists a realm of iron and motion that generates one of the most powerful forces on our planet. It's not gravity. It's not the force that holds atoms together. It's magnetism. Specifically, the enormous magnetic field generated by Earth's rotating iron core. And this field is the second line of defense against cosmic rays, the intimate protection that allows life to flourish on our world's surface. To understand Earth's magnetosphere, you need to first understand what's happening at the planet's heart. Imagine descending through Earth. You begin at the surface, in the cool air. You penetrate the crust, a layer of solid rock perhaps 30 kilometers thick on average, though it varies from place to place. You pass through the Mohorovich discontinuity, the boundary between crust and mantle, and enter the mantle itself, a layer of rock so hot that it flows slowly, like incredibly viscous honey, over timescales of millions of years. You keep descending,
The temperature rises. At 1,000 kilometers depth, the temperature reaches about 1,300 Kelvin. That's roughly 1,000 degrees Celsius. At 2,900 kilometers depth, you reach the core mantle boundary and the temperature jumps dramatically. You're now at approximately 4,000 Kelvin, hot enough to melt most metals. But the core doesn't melt, at least not all of it. The outer core, extending from about 2,900 kilometers to about 5,100 kilometers beneath the surface, is a liquid ocean of iron and nickel, superheated by the radioactive decay of uranium, thorium, and potassium. The convection in this liquid core is turbulent and chaotic, driven by heat flowing upward from the inner core and by the Coriolis effect created by Earth's rotation. The inner core, deeper still, extending from 5,100 kilometers to Earth's center at 6,371 kilometers, is a sphere of solid iron and nickel. It remains solid despite temperatures reaching about 5,200 Kelvin, hotter than the surface of the Sun, because of the immense pressure crushing down from all the material above it. The iron here is squeezed so tightly that it cannot melt, no matter how hot it becomes. This dichotomy, a solid inner core surrounded by a liquid outer core, is the key to understanding Earth's magnetism.
In 1905, a scientist named Joseph Larmor proposed a hypothesis that took decades to gain acceptance. Earth's magnetic field is generated by the circulation of liquid iron in the outer core. The mechanism is called the geodynamo, and it's a beautiful example of how a simple physical principle, the interaction between convection, rotation, and electrical conductivity, can produce profound effects. Here's how it works. Iron is an excellent electrical conductor. As the liquid iron in the outer core circulates, driven by convection currents, it moves through Earth's existing magnetic field, which itself was generated by previous convection. When a conductor moves through a magnetic field, an electrical current is induced in that conductor. This is Faraday's law of electromagnetic induction. The induced currents generate their own magnetic field, which affects the motion of the conducting fluid, which affects the currents, which affects the field. It's a feedback loop that sustains and amplifies itself. The result is that Earth's outer core acts like a dynamo, an engine that converts kinetic energy, the motion of the convecting iron, into magnetic energy, the planetary magnetic field. The field itself is generated by electrical currents in the liquid iron flowing around the inner core. This system is remarkably resilient. Even though Earth's core is cooling slowly, losing heat to the overlying mantle, convection continues. Radioactive decay in the core provides additional heat, and the rotation of the planet provides the Coriolis effect that organizes the chaotic convection into larger-scale circulation patterns. As long as these factors persist, the geodynamo will continue to operate. But here's something crucial. The magnetic field generated by the geodynamo extends far beyond Earth's surface. It reaches out into space, creating a region called the magnetosphere, a vast three-dimensional bubble of magnetic influence surrounding the planet. The solar wind, remember, is constantly streaming outward from the Sun at hundreds of kilometers per second. When this stream of charged particles encounters Earth's magnetic field, something remarkable happens. The solar wind is deflected. It cannot penetrate the magnetic field lines. Instead, it's forced to flow around the planet, creating a cavity, a zone of relative calm on Earth's day side, where the solar wind's pressure is balanced by the magnetic field's pressure.
This boundary between the solar wind and the magnetosphere is called the magnetopause. On Earth's day side, the side facing the Sun, the magnetopause is located at roughly 10 Earth radii,
about 60,000 kilometers from Earth's center, or roughly 54,000 kilometers above the surface. This distance is not fixed, it fluctuates with solar activity. During periods of intense solar wind pressure, coronal mass ejections, for example, the magnetopause is pushed inward. During quiet solar conditions, it expands outward. On the night side of Earth, the magnetosphere extends much farther. The solar wind drags magnetic field lines with it, stretching them into a long tail that extends far beyond Earth, in some cases out as far as the Moon's orbit. This is called the magnetotail, and it's an asymmetrical, dynamic region where magnetic reconnection events occur, releasing energy in spectacular auroral displays visible from Earth's surface as the northern and southern lights. Now, here's the critical question. How much protection does the magnetosphere actually provide against cosmic rays? The answer is nuanced. For lower-energy cosmic rays, those with energies less than a few billion electron volts, the protection is substantial. These cosmic rays are relatively easy to deflect or trap in the magnetosphere. The magnetosphere acts like a shield, keeping them away from the atmosphere and surface. But for high-energy cosmic rays, particularly the ultra-high energy ones, with energies exceeding 1 trillion electron volts, the magnetosphere's protection becomes almost negligible. These particles carry so much momentum that the magnetic field cannot significantly deflect them. They punch through the magnetosphere relatively undeterred, reaching Earth's atmosphere. So, while the magnetosphere provides excellent protection against lower-energy cosmic rays, it's almost transparent to the most energetic ones. This is important because it means that even with a fully functional magnetosphere, a fraction of the cosmic ray flux still reaches Earth's surface. The magnetosphere reduces but does not eliminate our exposure. However, and this is where it becomes very significant for our story, when the magnetosphere weakens or fails, even the lower-energy cosmic rays get through. And there's a time in Earth's history, a time that occurs roughly 200,000 to 300,000 years on average, when the magnetosphere undergoes a dramatic transformation, a magnetic reversal.
Imagine if tomorrow morning Earth's magnetic field suddenly reversed. The North Magnetic Pole and the South Magnetic Pole switched places. Compass needles would start pointing south instead of north. The entire magnetosphere would be reorganized. But more importantly for cosmic rays, during the transition from one magnetic polarity to the other, the magnetic field doesn't simply flip instantly. Instead, it passes through a period of chaos lasting hundreds or thousands of years. We call this the reversal transition. During this transition, the magnetic field strength may drop to 10% or less of its normal value, and the field structure becomes highly irregular, with multiple magnetic poles appearing simultaneously. When the magnetosphere weakens this dramatically, cosmic ray flux at Earth's surface increases substantially. Estimates suggest that during a full magnetic reversal, cosmic ray exposure at sea level might double or triple, and at high altitudes, where cosmic ray exposure is already higher, the increase could be even more dramatic. How do we know this happens? The evidence is written in the rocks themselves. As magma erupts from Earth's interior and cools, iron minerals within it align themselves with Earth's magnetic field at the moment of cooling. Once the rock solidifies, that magnetic alignment is frozen in place. It becomes a fossil record of Earth's magnetic field.
By measuring the magnetization of ancient volcanic rocks and sediments, geologists have been able to reconstruct Earth's magnetic field history over hundreds of millions of years. What they've discovered is striking. Earth's magnetic field has reversed polarity thousands of times throughout geological history. The reversals are not regular. Sometimes thousands of years elapse between reversals, sometimes only tens of thousands of years. But they're frequent enough that they represent a significant pattern in Earth's environmental history. The last magnetic reversal, called the Bruns-Motoyama reversal, occurred approximately 780,000 years ago. Before that, reversals occurred at intervals of roughly 200,000 to 300,000 years, though the intervals are highly variable. We're currently in the Brunskron, a period of normal polarity that has lasted longer than the average. If history is a guide, we're due for another reversal, though they cannot be predicted precisely.
Here's where the story becomes speculative but tantalizing. Did magnetic reversals influence the evolution of life on Earth? When the magnetosphere weakens during a reversal, not only do cosmic rays increase at the surface, other radiations also increase. Ultraviolet radiation from the sun, normally filtered by the ozone layer, becomes harder to completely shield. The upper atmosphere becomes more ionized. The chemistry of the atmosphere changes. For organisms at high latitudes or at high altitudes, organisms living in thin atmosphere or in water where UV penetration is limited, the increased radiation during a reversal would represent a significant stress. Mutations would increase. Some organisms would thrive, others would struggle. Some species might go extinct, others might evolve new traits. Paleontologists have examined extinction records to see if they correlate with magnetic reversals. The data is complex and not entirely conclusive, but some studies suggest a weak correlation, a slight increase in extinction rates during periods of frequent magnetic reversals, a decrease during periods of infrequent magnetic reversals. Nothing definitive. Many other factors influence extinction rates, but suggestive. More intriguingly, studies of organisms living during magnetic reversals, as recorded in ancient sediments, show evidence of increased mutation rates and developmental abnormalities during the reversal transition periods. It's not severe, life doesn't simply stop, but there's measurable stress. What we're beginning to see is a layered protection system. The sun's heliosphere provides the first shield, filtering out a significant portion of cosmic rays trying to reach the inner solar system. Earth's magnetosphere provides the second shield, deflecting the remaining cosmic rays and protecting the lower atmosphere and surface from the worst of the radiation. But both shields are imperfect. Both fluctuate. The heliosphere waxes and wanes with the solar cycle and experiences grand minima. The magnetosphere weakens during reversal transitions. When both shields are strong, cosmic ray exposure at Earth's surface rises substantially. For organisms living through such periods, this represents an environmental stress unlike any other in ordinary times. It's not as catastrophic as an asteroid impact or a supervolcanic eruption, but it's real. It's a force pushing on evolution, creating variation and selection pressure. The question we must now ask is, how have organisms responded to this recurring stress? How does life survive cosmic ray bombardment? What defenses do cells have? And could exposure to cosmic rays have actually promoted certain evolutionary developments, selected for traits that made our ancestors more resilient, more adaptable, ultimately more human? To answer these questions, we need to descend to the atomic scale, to the realm of molecules and DNA, where cosmic rays deposit their energy and where the fundamental damage and possible opportunity begins.
We've now established that Earth exists within a nested system of protective shields.
The Sun's heliosphere filtering cosmic rays from across the galaxy, and Earth's magnetosphere deflecting particles that slip through. But shields are only as good as their weakest moments. And in Earth's history, there have been periods, recurring, predictable periods, when both shields simultaneously weaken, when the cosmic ray flux reaching Earth's surface spikes dramatically, creating windows of time when life experiences radiation stress unlike anything in the ordinary rhythms of planetary habitability. To understand when these shield failures occur, we need to think about timescales, the overlapping cycles that govern cosmic ray exposure on our world. The layered timescales of cosmic ray exposure. Imagine 3 clocks, all ticking simultaneously, each one measuring a different rhythm. The fastest clock ticks every 11 years. This is the solar cycle, the rhythm of sunspot activity and solar magnetic field strength that modulates cosmic rays with a period of roughly 11 years, though the actual interval varies from about 9 to 14 years. The second clock ticks on a much longer timescale, the grand solar minimum cycle. This is not as regular as the 11-year cycle, but observations and ice core records suggest that periods of reduced solar activity, grand minima, occur episodically, perhaps once or twice per 1,000 years on average, though the frequency and duration vary. A grand minimum might last several centuries, during which the Sun produces fewer sunspots, the magnetic field weakens, and cosmic ray flux at Earth increases by perhaps 5% to 10%. Now here's the crucial insight. These clocks sometimes synchronize. What happens when a grand solar minimum coincides with a magnetic reversal transition? What happens when Earth passes through a galactic spiral arm where the baseline cosmic ray flux is elevated while simultaneously experiencing both a solar minimum and a magnetic reversal? These confluences are rare on human timescales, but over millions of years they become significant. They create periods of extraordinarily elevated cosmic ray exposure, cosmic ray storms that last for thousands or tens of thousands of years. And during these storms, evolution accelerates.
Let's begin with the longest timescale, the galactic spiral arms. Our solar system takes approximately 230 million years to orbit the galactic center. As it orbits, it periodically passes through the Milky Way's spiral arms, regions where star formation is active, where supernovae are frequent, where the background cosmic ray flux is naturally higher than in the quiet regions between spiral arms. Estimates based on our current understanding of galactic structure suggest that Earth's solar system passes through significant spiral arms roughly 100 to 150 million years. Each passage might last 5 to 10 million years. During such a passage, the baseline cosmic ray exposure reaching Earth is elevated, perhaps 50 to 100% higher than during interarm periods. How do we know this? The evidence comes from geological and paleontological records. Researchers have examined extinction rates, biodiversity patterns, and fossil records over the past 600 million years and compared them to models of spiral arm passages. Some studies identify correlations, periods of elevated extinction rates, periods of reduced biodiversity, periods of accelerated evolutionary change, all correlating with calculated spiral arm passage times. One prominent study suggested that several major extinction events in Earth's history coincide with spiral arm passages. These correlations are statistical and not perfectly consistent. Many other factors influence extinction and evolution, but they're suggestive. The idea is that during spiral arm passages, the increased cosmic ray exposure doesn't directly cause extinctions. The effect isn't that catastrophic, but it does increase environmental stress, increase mutation rates, potentially increase disease susceptibility due to immune system stress, and create selection pressures that favor adaptation evolution. Think of it as evolution under pressure. Species living during spiral arm passages experience a harsher cosmic radiation environment than those living during quieter times. Some species adapt and diversify, others decline. The overall pace of evolutionary change quickens. Now consider the magnetic reversal cycle. On average, a reversal occurs every 200,000 to 300,000 years. The reversal transition itself, the period during which the field strength is compromised and polarity is undefined, lasts roughly 1,000 to 10,000 years, depending on the specific reversal. During these transitions, Earth's magnetosphere loses its effectiveness. Cosmic ray flux at the surface increases substantially. High-altitude aircraft experience elevated radiation doses. If humans were exposed to equivalent radiation over the course of a day or a week, it would be hazardous. But distributed over thousands of years, the effect on human genetics would be small, perhaps a few extra mutations per generation. But for species living through multiple reversals over millions of years, the cumulative effect is measurable. Paleontologists have examined this question directly. By studying fossil records in sedimentary layers corresponding to magnetic reversal transition periods, researchers have found evidence of increased mutation rates, developmental abnormalities such as skeletal malformations, and changes in population structure during reversals. The organisms survived. Reversal transitions are not extinction events, but they experienced stress.
More intriguingly, some researchers have hypothesized that organisms evolve enhanced DNA repair mechanisms during periods of frequent reversals. If you're a species living through a magnetic reversal every 50,000 years, experiencing repeated episodes of elevated radiation exposure, natural selection would favor individuals with more effective DNA repair. Over many generations, such selection could lead to the evolution of more robust cellular defenses against radiation. This is speculative, but it's grounded in sound evolutionary logic. Increased environmental stress selects for traits that confer resistance to that stress. Let's consider a more recent example, one with better historical documentation, the Maunder minimum, which lasted from approximately 1645 to 1715. During this 70-year period, sunspot activity essentially vanished. Historical records, detailed astronomical observations by Johannes Hevelius, Gottfried Kirch, and other astronomers of the era document the dramatic absence of sunspots. Days would pass, weeks would pass without a single sunspot observed. When sunspots did appear, they were noted as exceptional events worthy of special record. The absence of sunspots correlates with a weakening of the sun's magnetic field and a reduction in the solar wind's strength. The interplanetary magnetic field weakened. Cosmic ray flux at Earth increased, as documented by elevated levels of carbon-14 in tree rings and beryllium-10 in ice cores from that era. The climate consequences were dramatic. The Maunder minimum coincided with the coldest part of the Little Ice Age. Temperatures in the northern hemisphere dropped by roughly 0.4 to 1 degree Celsius, not massive by today's climate change standards, but significant enough to cause agricultural disruptions, failed harvests, social upheaval, and famine in some regions. But did the increased cosmic ray exposure cause genetic catastrophes? This is harder to document, but there are hints.
Some researchers have found evidence in historical records of increased disease rates during the Maunder minimum, though causation is difficult to establish definitively. Other factors, such as increased poverty due to cold-related crop failures, also increase disease. What's clear is that the increased cosmic ray exposure didn't cause obvious genetic catastrophes. Humans survived the Maunder minimum, but the increased radiation background was a real environmental factor that organisms had to cope with.
The truly significant periods for evolutionary influence occur when these different timescales converge. When a solar grand minimum coincides with a magnetic reversal transition, and both occur during a galactic spiral arm passage. Such convergences are rare. A random grand minimum might occur while the field is normal. A random reversal might occur during a quiet solar era. But occasionally, perhaps once every few million years, all three conditions align. In those rare windows, cosmic ray exposure at Earth's surface spikes to levels perhaps 3 to 5 times higher than the baseline modern level. Such periods would last thousands to tens of thousands of years. They would represent an environmental stress unique in intensity, though not catastrophic enough to cause mass extinction. But for organisms living through such a period, the radiation environment would be substantially different from what they experience in ordinary times. And here's the key evolutionary implication. Such periods would create strong selection pressure for traits that provide radiation resistance or that benefit from genetic variation. Organisms with effective DNA repair mechanisms would have an advantage. Organisms with enhanced immune systems, necessary because increased radiation can compromise immunity, would fare better. And more broadly, the increased mutation rate would generate variation, and natural selection would act on that variation. Evolution doesn't require a steady state. Evolution accelerates under pressure. And cosmic ray exposure is a pressure that has waxed and waned throughout Earth's history. How do we know these shield-weakening periods actually influenced life? The evidence is indirect but compelling. Paleontologists have identified periods in Earth's history when extinction rates increased, when evolutionary innovation accelerated, when new body plans emerged, when biodiversity expanded unusually rapidly. When researchers map these periods onto models of galactic spiral arm passages and magnetic reversal frequencies, they find correlations. Not perfect correlations, evolution is too complex for that, but statistical associations that suggest a connection. For example, the Cambrian explosion, roughly 540 million years ago, when animal phyla diversified explosively, occurred during a period of relatively frequent magnetic reversals. The Ordovician radiation, another period of rapid diversification, coincides with modeling predictions of a spiral arm passage. Are these coincidences? Possibly, but they're suggestive. More recent evolutionary innovations also show hints of correlation with shield-weakening periods. The emergence of new primate species, the evolution of bipedal hominins, the rapid expansion of human brain size all occurred during periods characterized by more frequent magnetic reversals, or, in the case of recent human evolution, during a period of relatively elevated baseline cosmic ray exposure from a spiral arm passage. This brings us directly to the central concern of our narrative, human evolution. Humans and our hominin ancestors evolved during a particular era in Earth's history, an era characterized by relatively frequent magnetic reversals and, importantly, during what appears to have been a spiral arm passage. The timeline is revealing. Our solar system's passage through a significant spiral arm is estimated to have occurred roughly from 60 million years ago to about 40 million years ago. This period saw the diversification of early primates and the establishment of primate orders. Our solar system then left the spiral arm, entering a quieter region of the galaxy, but there's evidence from cosmic ray isotope records and magnetic reversal patterns that we've been gradually re-entering another spiral arm over the past 5 to 10 million years. The emergence of the first bipedal hominins, the Australopithecines, occurred roughly 7 to 4 million years ago, right at the time when we were beginning to experience elevated cosmic ray exposure from re-entering a spiral arm. The rapid evolution of Homo species, the explosion of brain size in Homo erectus and later Homo species, occurred over the past 3 million years, solidly within a period of elevated galactic cosmic ray background. Is this coincidence? It's impossible to say definitively. Correlation is not causation, but the temporal alignment is striking. Human evolution, the emergence of the traits that make us human, bipedalism, expanded brain size, enhanced cognitive abilities, occurred during a period when cosmic rays were more abundant at Earth's surface than they are today.
The shield's weakness is real. When the sun weakens, when Earth's magnetic field falters, when the galactic background radiation surges, life experiences stress. Increased mutation rates create genetic damage and developmental abnormalities. Cancer rates would increase. Immune systems would be stressed. But stress is also an opportunity. Increased mutations mean increased variation. Natural selection acts on that variation, selecting for traits that provide advantage. Species that evolve mechanisms to cope with radiation stress, enhanced DNA repair, improved immunity, behavioral adaptations gain competitive advantage. And sometimes, by chance, mutations provide traits that prove advantageous beyond radiation resistance. A mutation that enhances DNA repair might also enhance cognitive function. A genetic change that improves radiation immunity might also improve overall fitness. This is the paradox of cosmic rays. They're a danger and an opportunity. A shield failure is a crisis and a catalyst. In our story, as humans evolved under the influence of elevated cosmic ray exposure during a period of weak shields and galactic spiral arm passage, they experienced this paradox directly. The radiation stress they experienced may have accelerated their evolution, driven selection for enhanced cognitive abilities, shaped their physiology and behavior. But to understand the mechanisms by which cosmic rays can influence evolution, we need to descend deeper, down to the molecular level, into the realm of DNA damage, mutation induction, and the cellular responses to radiation.
We've traveled from the scale of the galaxy down to the scale of the planet. We've explored the shields that protect us and the periods when those shields weaken. But now we need to make one final descent, from the planetary scale down to the molecular scale, into the heart of the cell, into the double helix of DNA itself. Because cosmic rays, for all their cosmic grandeur, ultimately exert their influence on evolution not through anything happening in the upper atmosphere, but through what happens when a high-energy particle collides with the most important molecule in all of biology, deoxyribonucleic acid, DNA. DNA is the instruction manual of life. Every gene you possess, every trait your body exhibits, every instinct that drives your behavior is encoded in the sequence of DNA in your cells. DNA is also extraordinarily vulnerable to radiation. Understanding how cosmic rays damage DNA and how cells respond to that damage is the key to understanding how cosmic rays could possibly have shaped human evolution. First, let's review what DNA is. The DNA molecule is a double helix, two long strands of nucleotides twisted around each other. Each nucleotide consists of three parts: a sugar, deoxyribose, a phosphate group, and four bases: adenine, A, guanine, G, cytosine, C, or thymine, T. The bases pair across the two strands. Adenine always pairs with thymine, guanine with cytosine, held together by relatively weak hydrogen bonds. The sequence of bases along the DNA strand encodes genetic information. Every three bases form a codon which specifies a particular amino acid. Genes are stretches of DNA that code for proteins. The human genome contains roughly 3.2 billion base pairs organized into about 20,000 to 25,000 genes distributed across 23 pairs of chromosomes. This structure is elegant and efficient, but it's also vulnerable. The chemical bonds holding DNA together are electromagnetic interactions, electrons in orbitals around atoms. When a high-energy cosmic ray particle crashes into a DNA molecule, it deposits its energy in the form of ionization events. Electrons are knocked out of their orbitals, creating ions, charged atoms with missing electrons. This ionization can break the chemical bonds in DNA. When a cosmic ray particle, typically a muon, a high-energy photon, or a secondary particle from a cascade, strikes a DNA molecule, the damage is immediate and severe. If the particle has sufficient energy, it can knock apart the covalent bonds that form the DNA backbone or that link base pairs. The most dangerous type of damage is called a double-strand break, DSB. This occurs when both strands of the DNA double helix are severed, often near the same location. Imagine cutting both strands of a rope ladder with scissors. The ladder falls apart. A double-strand break essentially severs the chromosome into pieces. Without repair, the genetic information on that chromosome is lost. A single cosmic ray particle traveling through a cell nucleus might cause multiple double-strand breaks. High-energy heavy ions, like iron nuclei in cosmic rays, are particularly damaging because they're more massive and deposit their energy over a shorter distance, creating intense tracks of ionization. A single heavy-ion cosmic ray can cause a dozen or more double-strand breaks in a single cell nucleus. Single-strand breaks are also common, breaks affecting only one strand of the helix. These are generally less severe because the unbroken strand serves as a template for repair. But accumulation of many single-strand breaks in a small region can be as damaging as a double-strand break. Base damage is another form of direct damage. When an ionization strikes a DNA base directly, it can alter the base's chemical structure, turning an adenine into something that's no longer adenine, potentially changing which base it pairs with during DNA replication. But the damage isn't limited to direct hits. Cosmic rays ionize many other molecules in the cell, including water molecules. Water is ubiquitous in cells. Roughly 70% of a cell's mass is water. When a cosmic ray ionizes water, it creates highly reactive intermediates, free radicals, atoms or molecules with unpaired electrons that are chemically unstable and eager to react with other molecules. These free radicals can diffuse through the cell and collide with DNA, damaging it indirectly. A cosmic ray might ionize a water molecule a few nanometers away from a DNA strand, creating a hydroxyl radical, OH-, which then drifts through the cell and damages the DNA. This indirect damage is actually the dominant source of radiation damage in cells when exposed to moderate radiation doses.
It's why cells contain antioxidants and free radical scavengers, molecules like glutathione and superoxide dismutase, to neutralize free radicals before they can damage DNA. When a cell detects DNA damage, it activates an emergency response. This response is called the DNA damage response, DNR, and it's one of the most sophisticated systems in biology. First, sensor proteins detect the damage. Proteins like ATM, ataxia telangiectasia mutated, and ATR, ATM and RAD3 related, recognize double-strand breaks or other DNA lesions and become activated. These proteins act as emergency dispatchers, sending signals throughout the cell. Once the alarm is raised, the cell activates repair machinery. For double-strand breaks, the cell has two main repair pathways. Non-homologous end joining, NHEJ, is the faster but less accurate repair system. It works by recognizing the two broken ends of DNA, processing them slightly, and gluing them back together with specialized proteins like DNA ligase. NHEJ can repair a double-strand break in minutes. However, it's error-prone. Sometimes it removes a few base pairs or adds them back in incorrectly. This can lead to mutations. Homologous recombination, HR, is slower but more accurate. It works by using a homologous DNA sequence, often from the sister chromosome, as a template for correct repair. HR is more accurate than NHEJ, but it requires the cell to be actively dividing and have access to a homologous template. It typically takes longer, hours to days. For single-strand breaks and base damage, the cell uses other repair systems. Base excision repair, BER, removes altered bases and fills in the gap. Nucleotide excision repair, NER, removes stretches of damaged DNA. And match misarray, MMR, fixes errors in DNA replication. Here's where evolution enters the picture. When a cell detects DNA damage, it faces a critical decision point. If the damage is minor and can be accurately repaired, the cell repairs it and continues functioning normally. No mutation results. If the damage is extensive and cannot be accurately repaired, the cell faces two possibilities. It can attempt repair using error-prone mechanisms, accepting a small risk of mutation, or it can trigger apoptosis, a process of controlled death in which the cell essentially sacrifices itself to prevent the damaged DNA from being passed on. For germ cells, sperm and egg cells, the stakes are higher. A mutation in a germ cell will be inherited by offspring. Most mutations are neutral or mildly harmful, but some might be beneficial, and over many generations, beneficial mutations accumulate, driving evolution.
For somatic cells, body cells that don't pass on their genes, a mutation is less consequential for evolution, but more consequential for the individual. A mutation in a somatic cell could lead to cancer if it occurs in genes controlling cell division. When repair goes awry and a cosmic ray-induced DNA lesion isn't accurately fixed, the result is a mutation. Mutations can be classified by their size. Point mutations affect a single base pair. If the repair system misinserts a base when repairing a lesion, a point mutation results. AT might become GC, for example. Most point mutations are silent. They don't change the amino acid sequence of a protein due to the redundancy of the genetic code. A few point mutations are nonsense mutations. They create a stop codon, truncating the protein prematurely. Insertions and deletions occur when repair removes a few bases or adds extra bases. These can cause frame shift mutations if the number of bases inserted or deleted is not a multiple of 3. The reading frame for codons shifts, potentially changing the amino acid sequence of all downstream amino acids.
Chromosomal rearrangements occur when double-strand breaks are repaired incorrectly, joining breaks from different chromosomes or reversing a segment of a chromosome. Large-scale rearrangements can be highly detrimental, but occasionally they create new gene structures or regulatory arrangements with interesting properties. Here's a critical question. How much does cosmic ray exposure actually increase mutation rates? Studies in laboratory settings using artificially enhanced radiation show that mutation rates increase approximately linearly with radiation dose, at least for moderate doses. Doubling the radiation dose roughly doubles the mutation rate, tripling it roughly triples it. During periods of elevated cosmic ray exposure, such as during a magnetic reversal transition or a galactic spiral arm passage, mutation rates at the organismal level would increase correspondingly. If surface cosmic ray flux doubles, mutation rates roughly double. But here's the important nuance. The baseline mutation rate in humans is already quite high. Each individual accumulates roughly 0.1 to 0.5 new mutations per generation, new mutations that weren't present in either parent. The gametes, sperm and egg cells, experience about 100 to 300 radiation-induced double-strand breaks per cell division, though most are accurately repaired. During normal times, with normal cosmic ray exposure, most of these breaks are repaired accurately. But occasionally, maybe once in a million repairs, an error occurs and a mutation becomes fixed. During periods of elevated cosmic ray exposure, the number of repair events increases, so the number of errors increases proportionally. Mutations in germ cells, mutations that occur in sperm, eggs, or the cells that produce them, are heritable. They're passed to offspring. These are the mutations that drive evolution. When germ cells experience increased cosmic ray exposure during high radiation periods, the mutation rate in offspring increases. Mutations in somatic cells, in the hundreds of different cell types making up your body, are not inherited. They affect only that individual. However, somatic mutations can cause cancer if they occur in genes controlling cell division. Increased cosmic ray exposure would increase cancer rates. For the question of cosmic rays influencing human evolution, we're primarily concerned with germline mutations. Increased cosmic ray exposure during high radiation periods would increase germline mutation rates, increase genetic variation in populations, and therefore increase the variation available for natural selection to act upon. Here's where the evolutionary implications become profound. Imagine a population of early hominins living during a period of elevated cosmic ray exposure. Their gamete-producing cells are experiencing more radiation damage, experiencing more repair events, producing more mutations. Most of these mutations are neutral. They don't affect fitness either way. Many are mildly harmful. They reduce fitness slightly. But some are beneficial. A mutation that enhances cognitive function, a mutation that improves immune response, a mutation that enhances physical endurance. In a normal environment with low mutation rates, these beneficial mutations might be extremely rare, arising only once in a million births. But during a period of elevated cosmic ray exposure, if mutation rates double, then beneficial mutations arise twice as frequently. Natural selection acts on this increased variation, selecting for beneficial traits. Over many generations, thousands or tens of thousands of generations, this continuous selection, acting on an enhanced mutation pool, could accelerate evolution. Traits that provide advantages in the high radiation environment would spread through the population. Traits that require enhanced DNA repair or enhanced immunity would be selected for. This is the mechanism by which cosmic rays could have shaped human evolution, not through catastrophic events, but through a long-term increase in mutational input during periods when Earth's protective shields were weak and cosmic ray exposure at the surface was elevated. Of course, this mechanism comes with a cost. Elevated cosmic ray exposure doesn't just produce beneficial mutations, it produces harmful ones too. Cancer rates increase, genetic diseases increase. Many organisms would struggle with the radiation stress. But for populations with effective DNA repair mechanisms, with robust immune systems, with the physiological capacity to tolerate increased mutation rates, the benefit can exceed the cost. The enhanced genetic variation from increased mutation becomes fuel for adaptive evolution. This is particularly true when environmental conditions are otherwise challenging, when the climate is changing, when food sources are uncertain, when competition with other species is intense. In such environments, rapid evolution through increased mutation might be exactly what a species needs to survive and adapt. And this brings us directly to the context in which human evolution occurred, the African savanna, roughly 7 to 4 million years ago, a time of environmental instability, habitat fragmentation, and dietary transitions. It was during this period that the first bipedal hominins emerged. Could the elevated cosmic ray exposure from a galactic spiral arm passage have provided the mutational fuel that allowed or even facilitated the evolutionary innovations that produced the hominin lineage?
We've descended from the galaxy to the planet to the DNA molecule itself. But now we need to travel even deeper, not deeper in space, but deeper in time. Back to the very origins of life on Earth, back to a moment 4 billion years ago when the first organic molecules were assembling on a lifeless world. And we need to ask a question that seems almost absurd on the surface, but becomes profound upon reflection. Why do all living things use the same molecular handedness? This question, seemingly obscure, seemingly irrelevant to human evolution, is actually central to understanding how cosmic rays might have influenced not just the evolution of humans, but the emergence of life itself. And the answer involves one of the most peculiar phenomena in biochemistry, chirality, and its role in the origin of life. Handedness in molecules, left-handed and right-handed. Hold up your left hand and your right hand. They look similar. They have the same structure, thumb, 4 fingers, palm. But they're not identical. Your right hand is the mirror image of your left. You cannot superimpose one on the other. If you try to place your left hand on top of your right with palms touching, the thumbs point in different directions. Molecules can have this same property. Some molecules come in 2 forms, a left-handed version and a right-handed version. These are called enantiomers, and the property of existing in these 2 forms is called chirality. The word comes from the Greek chir, meaning hand. For molecules made of carbon, chirality arises when the carbon atom has 4 different atoms or groups attached to it. The arrangement of these attachments around the carbon can occur in 2 ways, one mirroring the other, producing left-handed and right-handed versions of the same molecule. Now, here's something crucial. In chemical reactions in the laboratory, when you synthesize a chiral molecule, you typically get a mixture, roughly 50% left-handed and 50% right-handed.
This is called a racemic mixture, and it's what you'd expect from basic chemical principles. There's no reason for one-handedness to be favored over the other. But life is different. All known life uses left-handed amino acids and right-handed sugars. Every protein in every living thing, from bacteria to humans, is made from left-handed amino acids. Every DNA and RNA molecule in every living organism contains right-handed sugars, ribose and deoxyribose. This is called homochirality, the dominance of a single chirality throughout the biological world. And it's one of the deep mysteries of biology. Why this handedness? Why not the opposite? How did life choose a particular chirality? Scientists have proposed numerous explanations for homochirality. One proposal involves autocatalytic reactions. Perhaps early in Earth's history, a racemic mixture of amino acids spontaneously formed, but by chance, left-handed amino acids began to be incorporated into primitive proteins more efficiently than right-handed ones. This would create a feedback loop. Left-handed amino acids would be preferentially used, enhancing the advantage of left-handedness, until eventually the system became locked into left-handed homochirality. But this explanation has problems. It requires an improbable sequence of events and doesn't explain why the system would switch to a consistent handedness rather than remaining mixed. But there is one force that could create such an advantage: cosmic rays. Here's a remarkable fact that physicists discovered in the 1970s. Radiation from certain astronomical sources, particularly radiation from the dying cores of stars and from certain types of supernova explosions, produces circularly polarized light. This is light whose electric field oscillates in a spiral pattern rather than in a straight line. Circularly polarized light has a handedness. It can be left circularly polarized or right circularly polarized, and circularly polarized light interacts preferentially with molecules of a particular chirality. Left circularly polarized light is absorbed more strongly by right-handed molecules, while right circularly polarized light is absorbed more strongly by left-handed molecules. In the early solar system, before Earth formed, as the cloud of dust and gas from which the solar system coalesced was exposed to radiation from nearby stars, particularly from radiation from a nearby supernova or from circularly polarized cosmic radiation, that radiation would have preferentially destroyed molecules of one chirality, while leaving molecules of the opposite chirality intact. Imagine a mixture of left-handed and right-handed amino acids floating in space, being bombarded by right circularly polarized radiation from a nearby star. The right circularly polarized light would preferentially destroy left-handed amino acids, leaving right-handed ones intact. The mixture would become enriched in right-handed amino acids. But wait, we said life uses left-handed amino acids, not right-handed, so this should give us the wrong result. Unless the prebiotic organic material included right-handed amino acids that were destroyed, leaving behind left-handed ones that weren't absorbed by the particular circularly polarized radiation being used. Or, more likely, the circularly polarized radiation from multiple stellar sources had a net handedness. Perhaps left circularly polarized radiation was more abundant from the particular stellar neighborhoods where our solar system formed, that preferentially selected for left-handed amino acids.
This is where cosmic rays enter the origin of life story. Supernovae and other high-energy astrophysical events produce not just high-energy particles, cosmic rays, but also electromagnetic radiation, including circularly polarized light. If the solar system's neighborhood was illuminated by radiation from such events, the prebiotic chemical inventory would have been sorted by chirality. Meteorites, chunks of space rock that have fallen to Earth, preserve organic material from the early solar system. Analyzing meteorites, scientists have discovered amino acids, and remarkably, these meteoritic amino acids show a slight enrichment in left-handed forms. Some meteorites show 5 to 10% excesses of left-handed amino acids over right-handed ones. This is small, but it's significant. It suggests that cosmic processes, circularly polarized radiation from astronomical sources, actually did sort prebiotic molecules by chirality. When these meteorites fell to early Earth, they brought with them organic material enriched in left-handed amino acids. When life began to form, through whatever mechanism, whether in deep-sea hydrothermal vents, in tidal pools, or in other prebiotic habitats, the available chemical building blocks were already skewed toward left-handedness. The early life forms that emerged would naturally use the available left-handed amino acids. Once this became established, once life had evolved molecular machinery that specifically recognized and used left-handed amino acids, it became locked in. Any new life form that emerged would use the same handedness as all existing life. The handedness became fixed. This is profoundly important. The very chirality of life, the fact that we and all living things use left-handed amino acids, might ultimately derive from cosmic influences. Specifically, from circularly polarized radiation produced by stellar explosions and distributed across the galaxy billions of years ago. Without this cosmic influence sorting molecules by chirality, the origin of life might have involved a random choice of handedness, or might have involved both handednesses competing with no clear winner. But with cosmic rays and cosmic radiation biasing the prebiotic chemistry toward one chirality, life was handed, literally, a particular molecular architecture. And that molecular architecture has been conserved for 4 billion years. Every protein in your body, every piece of DNA in every cell carries the imprint of that ancient cosmic influence. You are made of left-handed amino acids because of radiation from distant stars that illuminated the early solar system. But the implications extend beyond just the origin of life. Chirality also affects how molecules interact with each other and with the environment, and this has fitness consequences for organisms. Enzymes, proteins that catalyze biochemical reactions, are exquisitely specific about the chirality of their substrates. An enzyme that processes left-handed amino acids won't effectively process right-handed ones. The enzyme has a binding pocket with a specific three-dimensional structure that accommodates one chirality but not the other. This specificity means that biological systems are optimized around a particular chirality. All the enzymes in your cells have evolved to work with left-handed amino acids. If you somehow had right-handed amino acids in your proteins, those proteins likely wouldn't fold correctly or wouldn't function properly. The mismatch would reduce fitness. This creates an evolutionary ratchet. Once life committed to left-handed amino acids and right-handed sugars, that commitment became reinforced. Any mutation that caused incorporation of right-handed amino acids would likely be deleterious. Evolution would select against such changes. The chirality would remain locked in. But circularly polarized radiation from cosmic sources isn't just a one-time phenomenon from the early solar system. Supernovae are ongoing events. High-energy astrophysical phenomena continue to occur.
Circularly polarized radiation continues to fill interstellar space, though in varying amounts depending on the distribution of nearby stellar explosions. During periods when circularly polarized radiation from astronomical sources is particularly abundant, such as during periods when our solar system is in a region with recent supernovae, or during times when massive star-forming regions are nearby, the prebiotic environment might experience enhanced cosmic sorting of molecular chirality. For existing life, which is already locked into a particular chirality, this doesn't directly matter. Life uses what it's already committed to. But it does mean that the cosmic radiation environment has a subtle influence on the chemistry of the environment. It could affect the stability of organic compounds, the survival of certain molecular species, the efficiency of certain chemical reactions. More speculatively, if complex prebiotic systems were to emerge at certain times and places in Earth's history, perhaps during times when conditions were becoming suitable for abiogenesis, if life emerged more than once, the chirality bias in the chemical environment would influence whether such systems could successfully transition to true life.
What's remarkable about homochirality is that it illustrates a deep principle. Life's molecular structure is not inevitable. It's contingent on cosmic history. The particular choice of left-handed amino acids and right-handed sugars appears to have been influenced by cosmic radiation. A different pattern of supernovae in the early solar system neighborhood, a different flux and polarization of cosmic radiation might have produced a different chirality. This is humbling in a way. Our molecules, the very stuff we're made of, bear the imprint of cosmic events that occurred billions of years before Earth formed. We are made of stardust in a very literal sense, not just because the atoms in our bodies were forged in stellar interiors, but because the molecular architecture assembling those atoms was shaped by radiation from dying stars. And here's the deeper implication for our narrative. If cosmic radiation influenced the emergence of life itself through its effects on molecular chirality, and if cosmic rays have influenced the evolution of life ever since through their effects on mutation rates and selection pressure, then cosmic rays have been intimately involved in shaping every aspect of biology for the entire history of life on Earth. From the molecular handedness of life's building blocks to the emergence of complex organisms to the evolution of humans, cosmic influences have been present at every stage. We are, in a profound sense, the product of cosmic history. Our evolution is not just shaped by local planetary conditions, it's shaped by events across the galaxy, by the deaths of distant stars, by radiation traveling across millions of years of empty space. This is the deeper context for asking, did cosmic rays specifically influence the emergence of humans? The answer is almost certainly yes, but not as a simple direct cause. Rather, cosmic rays have been an environmental factor throughout Earth's history, influencing mutation rates, creating selection pressures, occasionally accelerating evolution during periods of weak planetary shields. The emergence of humans was influenced by this cosmic background, just as all of life has been. But to understand how this influence manifested in human evolution specifically, we need to trace the history of life from its origins through the emergence of our species. And that journey begins with the question of how life first started.
We've established that cosmic rays influenced the very molecular handedness of life itself, biasing prebiotic chemistry toward left-handed amino acids through cosmic radiation billions of years ago. But the story doesn't end there. Cosmic rays didn't just influence life's molecular structure. They may have actively powered the chemical reactions that created life's first organic molecules.
They may have been, quite literally, the spark that ignited life on Earth. To understand this, we need to travel back to Earth's infancy, to a time before life existed, when our planet was a very different place. Picture Earth approximately 4.1 to 3.8 billion years ago, during the Hadean Eon, a time that planetary scientists named after Hades, the Greek underworld, because they imagined it to be hellish. The sun was slightly dimmer than today, about 70% of its current brightness, yet the atmosphere was thick with methane and other greenhouse gases, making Earth warmer than it would be otherwise, a phenomenon called the faint young sun paradox. Surface temperatures likely ranged from 0 to 50 degrees Celsius, warm enough for liquid water despite the dimmer sun. But this was no paradise. Cosmic radiation was more intense than today. Earth's magnetic field was weaker and less stable than now. The geodynamo was still establishing itself. The solar wind was more vigorous. The young sun's corona was more active, producing more energetic flares and coronal mass ejections. Earth's atmosphere was thin, mostly nitrogen with substantial amounts of methane, carbon dioxide, ammonia, and water vapor, but little oxygen and no ozone layer. Ultraviolet radiation from the sun poured down unobstructed onto the surface. There were no continental masses yet, or they were vastly smaller. The oceans covered most of the planet. There were likely active hydrothermal vents on the ocean floor, hot springs where superheated, mineral-rich water emerged from the Earth's interior, creating temperature and chemical gradients. And there was no life. The oceans contained dissolved minerals, salts, gases. The rocks contained iron oxides and other minerals, but there were no self-replicating systems, no metabolism, no information storage, nothing we would recognize as alive. Yet somehow, within perhaps 400 to 500 million years of Earth's formation, the earliest chemical evidence of life appears around 3.8 to 3.7 billion years ago. Life emerged. Life went from not existing to existing. How? In 1952, scientists Stanley Miller and Urey conducted a famous experiment. They set up a glass apparatus containing water, methane, ammonia, and hydrogen, a supposed early Earth atmosphere. They ran electrical sparks through the mixture to simulate lightning, a supposed energy source for chemical reactions on early Earth. After a week, Miller and Urey found that the apparatus contained organic compounds, amino acids, sugars, and other organic molecules. This was revolutionary. It demonstrated that the building blocks of life could be synthesized from inorganic precursors using energy from lightning. Since then, scientists have refined our understanding of prebiotic chemistry. We know that many energy sources could drive synthesis of organic molecules on early Earth: lightning, ultraviolet radiation, heat from hydrothermal vents, and critically for our story, cosmic ray radiation. Cosmic rays deposit enormous amounts of energy in the atmosphere and surface environments. A single high-energy cosmic ray can ionize millions of molecules, creating excited electronic states, free radicals, and high-energy intermediates. These high-energy species are chemically reactive and can drive organic synthesis. In the early Earth atmosphere, cosmic rays would have ionized atmospheric molecules, nitrogen, carbon dioxide, methane, and water vapor, creating free radicals and other reactive intermediates. These intermediates could then react with each other or with other atmospheric constituents to form more complex organic molecules. Laboratory experiments simulating early Earth conditions with cosmic ray radiation or with simulated cosmic ray effects using high-energy particle beams have shown that organic molecules can indeed be synthesized efficiently when cosmic ray energy is available. Amino acids, nucleotide bases, and other prebiotic organic molecules form. The cosmic ray flux on early Earth was higher than today for multiple reasons. The magnetosphere was weaker, the solar wind was more vigorous and less protective, and the atmospheric shielding was different. Scientists estimate that cosmic ray-induced ionization in the early atmosphere might be 2 to 10 times higher than today. This means that cosmic radiation was a significant energy source for prebiotic synthesis, perhaps comparable or exceeding lightning as an energy source for organic molecule formation. But the synthesis of organic molecules is just the first step. Getting from organic molecules to life requires a crucial transition, the emergence of self-replicating systems. Life, at its core, is a system that can make copies of itself. How did that happen? The answer likely involves RNA, ribonucleic acid. RNA is similar to DNA, but with important differences. It has a ribose sugar instead of deoxyribose, and it uses uracil instead of thymine. More importantly, RNA can fold into three-dimensional structures and can catalyze chemical reactions. Some RNA molecules, called ribozymes, can actually cut and splice themselves. Scientists propose the RNA world hypothesis. In the early Earth, before DNA and proteins evolved, RNA was the dominant form of genetic material. RNA molecules that could replicate themselves, that could serve as templates for making copies, would have multiplied. RNA molecules with catalytic properties could accelerate their own replication. Over time, through a process analogous to evolution, RNA sequences that replicated efficiently would become more abundant. Eventually, some RNA molecules would have acquired the ability to direct the synthesis of proteins through a primitive version of the modern genetic code. Proteins, being more chemically diverse than RNA and better suited for catalysis, could perform catalysis more efficiently. Eventually, DNA, which is more chemically stable than RNA and better suited for long-term storage, would evolve as the primary genetic material, with RNA relegated to an intermediary role and proteins handling most catalysis. This is the scenario, and while many details remain speculative, the basic framework is supported by extensive experimental evidence and theoretical modeling.
But how would the energy for these early self-replicating systems come from? Lightning is intermittent, hydrothermal vents are localized, ultraviolet radiation is available on the surface, but surfaces exposed to UV are also exposed to damaging radiation that can destroy organic molecules as fast as they form. Cosmic ray radiation provides a steady, continuous energy source. Unlike lightning, which is sporadic, cosmic rays rain down continuously, 24 hours a day, even in dark environments like the deep ocean or inside rock crevices, places where primitive life might actually form, protected from the harshest UV radiation. Cosmic ray ionization in the oceans would create reactive chemical species throughout the water column. These species could drive synthesis of organic molecules. They could also drive polymerization, linking small molecules into larger chains, and they could drive the chemical reactions necessary for RNA replication and protein synthesis. Moreover, cosmic ray-induced chemistry wouldn't be limited to the surface. In deep ocean environments, where hydrothermal vents provide chemical energy through oxidation-reduction reactions between hot mineral solutions and cold seawater, cosmic rays would penetrate from above, adding an additional energy source.
The RNA world hypothesis proposes that early life consisted of self-replicating RNA molecules. But RNA is a complex molecule. It's not trivial to synthesize spontaneously, even with energy input. How would the first RNA molecules form? Laboratory experiments have shown that cosmic ray radiation can indeed drive synthesis of RNA precursors, nucleotides and nucleotide bases from simpler precursors. Cosmic ray ionization creates the high-energy chemistry necessary to form these complex molecules. Once nucleotides are available, they can polymerize, link together to form RNA strands. This polymerization doesn't happen spontaneously in solution, but it can be catalyzed by mineral surfaces, by heat from hydrothermal vents, or by repeated cycles of wet-dry conditions, such as in tidal zones or around hot springs. The crucial point is that cosmic ray radiation provided the energy input that made the synthesis of prebiotic organic molecules, including RNA precursors, thermodynamically favorable. Without this energy source, the chemistry would be driven by other sources, lightning, heat, UV, but cosmic rays made it more efficient, more widespread, more relentless. This raises a fascinating question. How probable is the origin of life? If life required improbably rare events, then life might be vanishingly rare in the universe. But if the necessary chemistry is driven by abundant energy sources like cosmic rays, then life might be relatively common. By providing a continuous ubiquitous energy source throughout the early Earth environment, cosmic rays increased the probability that self-replicating systems would spontaneously form. The vast amount of cosmic ray energy being delivered to the oceans and atmosphere meant that the right chemistry, the chemistry necessary for life, would occur. Given enough reactions happening continuously, given trillions of molecular interactions every second due to cosmic ray ionization, it becomes increasingly probable that some of those interactions would produce an RNA-like molecule capable of self-replication. Once self-replication was established, natural selection would take over. Self-replicating molecules with small variations would compete. Those variations that enhanced replication accuracy or replication speed would become more abundant. Evolution would begin, even at the molecular level, before anything we'd call life yet existed. So, perhaps cosmic rays were not just a background factor in the origin of life, they were the spark. Lightning might have played a role, hydrothermal chemistry definitely did, but cosmic rays, by providing abundant energy throughout all environments, provided the sustained chemical complexity necessary for self-replication to emerge. Life on Earth might have arisen through the following sequence. Cosmic rays ionize the early atmosphere and oceans, driving synthesis of organic molecules, including nucleotides. These nucleotides polymerized into RNA-like strands, forming a vast chemical library of different sequences. Occasionally, by chance, one of these sequences could self-replicate. That replicator attracted building blocks, nucleotides, making copies of itself. Variants arose through errors in copying. Natural selection acted on those variants. Life began. In this scenario, cosmic rays were essential. Without them, the chemical complexity would have been lower, the formation of self-replicating systems less probable. Early life might have emerged much later, or perhaps not at all, if cosmic rays had been significantly weaker.
And here's the profound implication. If cosmic rays powered the origin of life, they didn't stop influencing life once it emerged. Cosmic rays continued to be an environmental factor, continuing to drive mutations through subsequent billions of years of evolution. Life originated in a cosmic radiation environment and evolved continuously within that environment. This means that the entire history of life on Earth, from the origin of the first self-replicating RNA molecules to the emergence of complex multicellular organisms to the evolution of humans, occurred within a cosmic radiation context. Cosmic rays didn't just create life, they have been shaping it ever since. We are not just the products of natural selection acting on random mutations. We are the products of natural selection acting on mutations partly induced by cosmic rays that have been influencing life's genetic variation for billions of years. This is the continuity we need to grasp. Cosmic influences on life's molecular structure through chirality, on life's origin through energy input for prebiotic synthesis, and on life's evolution through mutation induction and selection pressure. Each step in the chain connects back to cosmic processes. And as we move forward in our narrative, preparing to ask how cosmic rays might have specifically influenced human evolution, this continuity is essential to remember. Humans are not isolated from cosmic influences. We are embedded in a cosmic context. Our evolution is a chapter in the long story of how the cosmos has shaped life.
For billions of years, cosmic rays have rained down on Earth as a steady background radiation, influencing evolution through slow accumulation of mutations and selection pressure. But occasionally, rarely, the cosmic ray flux spikes dramatically, not due to changes in Earth's shields, but due to violent events happening across the galaxy. A massive star somewhere in the Milky Way explodes, a supernova. A supernova is one of the most catastrophic events in the universe. In the space of a few seconds, a star that has existed for millions of years destroys itself, releasing energy in a burst so bright that for a few weeks that single explosion can outshine an entire galaxy containing billions of stars. And in that explosion, a torrent of cosmic rays is created and hurled into interstellar space. To understand how supernovae can influence evolution on Earth, we need to understand what supernovae are, how they produce cosmic rays, and what happens when a nearby supernova floods Earth with radiation. We've already introduced one type of supernova in this narrative, the core collapse supernova that results from the death of a massive star. Let's revisit and expand that scenario. A massive star, say 20 times the mass of our Sun, burns through its nuclear fuel at a catastrophic rate. It lives fast and dies young. While our Sun will exist for 10 billion years, a star 20 times more massive will burn out in just 10 million years. In a few million years, it will have fused hydrogen into helium, helium into carbon and oxygen into silicon and iron. When the core becomes primarily iron, the star's fate is sealed. Iron fusion doesn't release energy, it consumes energy. The core can no longer support itself. Over the course of seconds, the core collapses catastrophically. The infalling material rebounds off the ultra-dense neutron-like material at the core, creating a shock wave that tears through the star's outer layers. The star explodes. This is a Type II supernova, also called a core collapse supernova, and it's one of the most violent events known. The explosion releases as much energy in a few seconds as the Sun will release in its entire lifetime. The expanding material reaches speeds of 30,000 kilometers per second, 10% the speed of light. The other major type of supernova is a Type Ia supernova, which occurs in binary star systems where a white dwarf, the ultra-dense remnant of a dead star, is orbiting a companion star. Material from the companion star falls onto the white dwarf's surface, accumulating until the pressure and temperature trigger thermonuclear fusion of the entire surface. The white dwarf explodes. Both types of supernovae produce enormous cosmic ray fluxes, accelerating particles to extreme energies through the expanding shock wave and intense magnetic fields. The mechanism by which supernovae accelerate cosmic rays is called Fermi acceleration.
It works like this. The expanding shock wave of the supernova explosion creates a thin boundary between hot material streaming outward and cold material not yet reached by the shock wave. In this boundary region, the magnetic field becomes extremely turbulent. Charged particles, protons and heavier nuclei that happen to enter the boundary get scattered by the turbulent magnetic field. Each scatter event can either increase or decrease the particle's energy, but statistically, particles that cross the boundary multiple times gain energy on average. Particles that escape the boundary do so with higher energy than they entered. Particles that re-enter get scattered again, potentially gaining more energy, creating a feedback loop. This process can continue as long as the shock wave is still expanding, and for Type II supernovae, shock waves can expand for weeks or months before they dissipate. The result is that particles are accelerated to ever higher energies, with the highest energy particles carrying energies of 1 trillion electron volts or more. So a supernova is not just an explosion, it's an engine for cosmic ray production. It's a particle accelerator of vast scale, powered by the energy of stellar death, flinging high-energy particles across the galaxy. After the initial explosion fades, the expanding material continues to move outward, creating an expanding shell of hot ionized gas and particles. This is called a supernova remnant. The Crab Nebula, created by a supernova observed by Chinese astronomers in 1054 CE, is a famous example. The expanding gas shell glows, energized by the energy released in the explosion and by radiation from a neutron star, a pulsar left behind at the center. Supernova remnants remain visible and energetic for thousands or tens of thousands of years. They continue to accelerate cosmic rays as the expanding shock wave works its way through the surrounding interstellar medium. Eventually, the remnant cools, slows, and dissipates into the interstellar medium, becoming indistinguishable from the ambient gas. But before that happens, the supernova has released a tremendous flux of cosmic rays into the galaxy. Some of those cosmic rays will eventually reach Earth, but the journey takes time. Cosmic rays travel through space, but they're deflected by magnetic field lines, so their paths are not straight. A cosmic ray produced in a supernova 10,000 light-years away might take millions of years to reach Earth, following a tortuous path through the galaxy. But eventually, some of those cosmic rays will reach us, and when they do, they cause a temporary spike in cosmic ray flux at Earth. How close would a supernova need to be to dramatically increase cosmic ray exposure on Earth? Scientists have estimated that a supernova occurring within about 100 light-years of Earth would produce a significant spike in cosmic ray flux, increasing cosmic ray exposure at Earth's surface by factors of 2 to 10 for periods of hundreds to thousands of years. This might sound like a safe distance. 100 light-years is enormous, but in the context of the galaxy, which is 100,000 light-years across and contains hundreds of billions of stars, 100 light-years is actually quite close. Astronomers estimate that on average, a supernova occurs somewhere in the galaxy every century or so. The probability of a supernova occurring within 100 light-years of Earth is roughly once in a few million years. This is frequent enough on evolutionary scales to matter.
When cosmic ray flux increases at Earth, one of the first consequences is ionization of the upper atmosphere. This has a cascading effect on atmospheric chemistry, particularly on the ozone layer. The ozone layer, a region of Earth's stratosphere where ozone, O3, is concentrated, protects life from ultraviolet radiation. UV radiation is damaging to DNA and proteins. Cells exposed to intense UV suffer mutations, cancer, and death.
The ozone layer absorbs most of the UV radiation before it reaches the surface, allowing life to exist on land. When cosmic ray flux increases, secondary cosmic ray particles ionize atmospheric gases in the stratosphere and mesosphere. This ionization affects boson chemistry. Cosmic ray-induced ionization creates odd nitrogen compounds, NOx, and odd hydrogen compounds, HOx, which are catalysts for ozone destruction. The result is a temporary depletion of the ozone layer. During a nearby supernova event, the ozone layer could be depleted by 10% to 50%, depending on how close the supernova was. This would allow more UV radiation to reach the surface. Organisms exposed to intense UV would suffer damage, increased mutation rates, increased cancer rates, potentially increased mortality. For microorganisms living in surface waters or on exposed rock surfaces, an ozone depletion event would be severely stressful. For animals, the increased UV would increase mutation rates, particularly in germline cells that would pass mutations to offspring. The increase in cosmic ray flux reaching Earth's surface during a nearby supernova event would vary depending on Earth's magnetic shield and other factors, but a reasonable estimate is that cosmic ray flux could increase by factors of 2 to 5 during the worst periods of a nearby supernova event. This would increase mutation rates at the surface correspondingly. An organism experiencing a 3-fold increase in cosmic ray exposure would experience roughly a 3-fold increase in radiation-induced mutations. For organisms at sea level in the tropics, where cosmic ray exposure is normally lowest, even a modest increase would be significant. For organisms at high altitudes or high latitudes, where cosmic ray exposure is already relatively high, a 3-fold increase would be extreme. The question becomes, did supernovae cause extinctions in Earth's history? Did nearby supernovae flood Earth with cosmic rays, increase mutation and disease rates, and drive species to extinction? The evidence is suggestive but not conclusive. Paleontologists have identified several periods of elevated extinction rates in Earth's fossil record. Some researchers have proposed that nearby supernovae could explain these events. One prominent study examined extinction patterns over the past 250 million years and compared them to modeled frequencies of nearby supernovae. The researchers found a statistically significant correlation. Periods of elevated extinction rates tended to correlate with times when nearby supernovae were predicted to have occurred. However, other researchers have challenged these correlations, pointing out that many other factors influence extinction rates: climate change, asteroid impacts, volcanic activity, sea level changes. Supernovae may be a contributing factor, but not the dominant one. The most compelling evidence for supernova influence on life comes not from extinction events, but from isotopic records. Cosmic rays interact with atmospheric oxygen and nitrogen, produce specific isotopes, beryllium-10 and carbon-14. These isotopes accumulate in ice and sediment layers. By analyzing isotope levels in geological samples from specific time periods, scientists can infer whether cosmic ray flux was elevated at that time. Some studies have identified elevated isotope levels corresponding to times when supernovae are predicted to have occurred nearby, suggesting that cosmic ray exposure did indeed increase during those periods.
One particularly interesting period in Earth's history, relevant to our story about human evolution, occurred roughly 375 to 360 million years ago, during the transition from the Devonian to the Carboniferous periods.
This period saw elevated extinction rates, particularly among marine organisms. It's called the Devonian extinction, or the late Devonian extinction event. Multiple causes have been proposed for the Devonian extinction: climate change, ocean anoxia, oxygen depletion, asteroid impacts. But some scientists have suggested that a nearby supernova or gamma-ray burst could have contributed to the extinction. Recent studies have analyzed isotope levels in sediments from the Devonian Carboniferous boundary and found evidence of elevated cosmic ray exposure during this period. The timing and magnitude suggest that a nearby supernova or similar high-energy event could have flooded Earth with cosmic rays, increased mutation rates, depleted the ozone layer, and created an environment of intense stress that contributed to elevated extinction rates. While a single supernova probably didn't cause the entire extinction event, it was likely a combination of factors. The evidence suggests that supernovae can have detectable effects on Earth's biosphere. But here's the key point for our narrative. Supernovae don't just cause extinctions, they create selection pressure. During periods when nearby supernovae are flooding Earth with cosmic rays, organisms experience intense radiation stress. Individuals with superior DNA repair mechanisms have an advantage. Individuals with enhanced immunity survive better. Individuals with genetic variations that confer radiation resistance are selected for. Over many generations, this creates evolutionary pressure favoring traits that confer radiation resistance. Populations evolve enhanced defenses against radiation. Some species may acquire mutations that, while not directly related to radiation resistance, happen to provide other advantages and become fixed because they arose during high radiation periods when mutation rates were elevated. Supernovae can therefore be drivers of evolutionary innovation, particularly in creating diversity in populations and selecting for enhanced robustness. For species with effective DNA repair mechanisms and flexible genomes, a nearby supernova event might be an opportunity as much as a threat. This brings us to a crucial question. During the millions of years when hominins were evolving, how many nearby supernovae occurred? The frequency of nearby supernovae varies depending on the star density in the region of the galaxy. Our solar system orbits in the galactic disk, where star density is moderate. In dense regions like the galactic center or in globular clusters, nearby supernovae would be more frequent. In sparse regions between spiral arms, they'd be rarer. Current estimates suggest that on average, a supernova occurs nearby within 100 light-years, roughly once every few million years. During the past 10 million years, a period spanning most of human evolution, we might expect 2 to 5 nearby supernova events. This means that during the emergence and evolution of the hominin lineage, our ancestors experienced at least a few periods when cosmic ray exposure spiked dramatically due to nearby supernovae. These would have been periods of intense evolutionary pressure, periods when mutation rates were elevated, when organisms experienced radiation stress, when selection favored enhanced robustness. Over tens of millions of years, this intermittent pressure, combined with the steady background pressure from galactic cosmic rays during periods of weak planetary shields, created an environment where evolution favored traits associated with genetic robustness, efficient DNA repair, and enhanced adaptability. These are precisely the traits that have become increasingly prominent in the primate lineage and particularly pronounced in the human lineage. We've explored how supernovae produce cosmic rays and how increased cosmic ray flux can stress organisms and alter evolution. But to truly understand the potential impact of cosmic rays on life, we need to examine a specific historical example, a real extinction event in Earth's history, where cosmic influences may have played a role. We need to look at the Devonian Carboniferous boundary, a period roughly 375 to 360 million years ago, when life on Earth experienced one of the most severe crises in its history. This event is particularly relevant to our narrative because it demonstrates that cosmic influences on life are not merely theoretical, they're recorded in the fossil record. And it provides a template for understanding how cosmic rays might have influenced later events, including the emergence of humans. To understand the Devonian extinction, we first need to understand what the Devonian world was like. The Devonian period, spanning roughly 419 to 359 million years ago, is often called the Age of Fishes because it was a time of extraordinary diversification and dominance of fish species. During the Devonian, the continents were arranged differently than today. The supercontinent Laurasia, comprising modern North America and Eurasia, was positioned near the equator. Gondwana, comprising modern Africa, South America, Antarctica, and Australia, was in the southern hemisphere. Between them lay the vast Paleotethys Ocean and other ocean basins. Shallow seas covered much of the continents, creating extensive coastal and near-shore environments. These shallow seas were teeming with life. Fish had already evolved jaws and fins, allowing them to become active predators and swimmers rather than passive filter feeders. Sharks and ray-finned fish were diversifying. Lobe-finned fishes, the ancestors of all tetrapods, four-legged vertebrates, were beginning to exploit shallow waters and coastal environments. Armored fish called placoderms were abundant. On land, plants had begun to pollinize. Early vascular plants, relatives of modern ferns, were establishing themselves in terrestrial environments, creating the first forests and the first substantial land ecosystems. Arthropods, the ancestors of modern insects, spiders, and crustaceans, were diversifying on land and in water. It was a world of expansion, of ecosystems filling ecological niches, of evolutionary innovation. And then something went terribly wrong. Roughly 375 million years ago, extinction began. In marine ecosystems, particularly in shallow seas and coral reef environments, species diversity began to decline. Not dramatically at first, but noticeably. Coral reefs that had thrived for millions of years began to decline. Trilobites, which had been dominant marine arthropods for hundreds of millions of years, became less diverse. Fish species began to disappear. This was not a sudden catastrophe, it was a protracted crisis lasting roughly 15 million years with multiple phases of extinction and recovery. Ecosystems would stabilize temporarily, then another wave of extinctions would strike. By the end of the Devonian and the beginning of the Carboniferous, around 359 million years ago, the damage was severe. About 75% of all animal species had gone extinct, one of the big 5 extinction events in Earth's history. Paleontologists have identified multiple contributing factors to the Devonian extinction. It was not a single event, but a cascade of environmental stressors. Climate change,
Sea level fluctuated dramatically during this period, with global ocean levels rising and falling by hundreds of meters. These fluctuations created cycles of flooding and exposure in shallow marine environments. Coastal habitats were repeatedly submerged and exposed, destabilizing ecosystems. Ocean anoxia. Periodic episodes of oxygen depletion occurred in marine basins. When water becomes depleted of oxygen, often due to increased organic matter decomposition or disrupted circulation, organisms suffocate. Anoxic events in the Devonian eliminated many species, particularly those in deeper waters with poor circulation. Asteroid impacts. Evidence suggests that one or more asteroid impacts may have occurred during the late Devonian. Impact craters of the right age have been identified. Asteroid impacts would have released energy and created dust clouds affecting climate. Supernovae events. Several independent studies have proposed that one or more nearby supernovae occurring around 375 to 359 million years ago could have contributed to the Devonian extinction. The reasoning was as follows. A supernova occurring within roughly 100 light-years of Earth would produce a measurable increase in cosmic ray flux. This increased cosmic ray flux would cause atmospheric ionization, leading to ozone depletion. The ozone depletion would allow intense UV radiation to reach the surface. Additionally, the increased cosmic ray flux itself would increase radiation exposure and mutation rates. The combined effect, increased cosmic ray exposure plus UV exposure from ozone depletion, would create an extremely stressful environment for surface-dwelling organisms. Extinction rates would increase, mutation rates would dramatically increase. To test this hypothesis, Mellett's team analyzed isotope records from the Devonian period. They looked for elevated levels of beryllium-10 and carbon-14, isotopes produced by cosmic ray interactions in the upper atmosphere. If supernovae had indeed flooded Earth with cosmic rays, these isotope levels should be elevated in geological samples from that time. The results were striking. Isotope levels in sediments from the Devonian Carboniferous boundary showed significant elevations consistent with a nearby supernova event. The timing and magnitude suggested that cosmic ray flux had increased substantially, roughly 2 to 3 times above baseline levels for a period of several hundred to a few thousand years. But how would a supernova-induced cosmic ray increase connect to ocean anoxia, one of the primary culprits in the Devonian extinction? The connection is indirect but plausible. Increased cosmic ray ionization in the atmosphere affects atmospheric and oceanic chemistry. Ionization creates reactive compounds that can alter the balance of gases in the atmosphere, affecting how oxygen and carbon dioxide are distributed. Additionally, the increased radiation and environmental stress might have affected ocean circulation patterns or biological productivity in ways that could lead to ocean anoxia. Some researchers have proposed that during periods of high cosmic ray exposure, the upper atmosphere's chemical composition changes in ways that affect the rate of oxygen production and carbon dioxide processing. These changes, multiplied across the entire biosphere over thousands of years, could potentially contribute to periods of ocean anoxia. This is speculative, but it illustrates how cosmic influences could be connected to broader environmental changes.
One of the most striking aspects of the Devonian extinction was the near-complete collapse of coral reef ecosystems.
Coral reefs had existed continuously since the Ordovician period, roughly 100 million years before the Devonian. Yet, during the late Devonian, reef ecosystems virtually disappeared. Reefs that had existed for millions of years went extinct within a geological eye blink. Coral reef ecosystems are sensitive to environmental stress. They require specific conditions: stable warm temperatures, clear water, moderate salinity, and adequate oxygen. They're dependent on their symbiotic relationship with zooxanthellae, photosynthetic organisms living in the coral tissues, which require adequate light. Any disruption to these conditions can cause reef stress and eventual collapse. During the Devonian extinction, multiple stresses hit reefs simultaneously: oxygen depletion, temperature fluctuations, increased UV exposure if ozone depletion occurred, sediment runoff, and potentially toxic compounds from enhanced atmospheric chemistry. Reefs couldn't survive this gauntlet of stresses. What makes this relevant to our cosmic ray hypothesis is that increased UV exposure from ozone depletion would be particularly devastating to reef ecosystems. The zooxanthellae living in the coral tissues are photosynthetic organisms that are sensitive to UV damage. Intense UV exposure would kill zooxanthellae, causing the coral to expel them, coral bleaching. Without zooxanthellae, corals starve as they depend on the sugars produced by their symbiotic partners. A supernova-induced ozone depletion event would therefore be particularly devastating to reef ecosystems, potentially explaining the near-total collapse of reefs during the Devonian. Fish were the dominant animals during the Devonian, and they were hit hard by the extinction. Many fish lineages went extinct, others survived but in reduced diversity. Yet fish overall recovered by the Carboniferous, diversifying again into various forms. Why would fish be particularly vulnerable to cosmic ray-induced extinction? Fish living in shallow seas would be exposed to increased UV radiation if ozone depletion occurred. Fish eggs and larvae, which are particularly vulnerable to UV damage, would suffer high mortality rates. Additionally, the increased cosmic ray exposure would increase mutation rates in fish populations, potentially creating genetic damage that reduced fitness. Fish in deeper waters would be more protected from both UV and cosmic rays, potentially giving them a survival advantage. This could explain why some fish lineages survived, while shallow water lineages collapsed. By the Carboniferous period, roughly 359 to 299 million years ago, life had recovered from the Devonian extinction. Ecosystems restructured, new dominant species emerged, fish diversified again into various forms. Tetrapods, four-legged vertebrates descended from lobe-finned fishes, began to colonize land more extensively. Insects underwent their first major radiation into diverse forms. Plants continued to evolve, with vascular plants becoming increasingly dominant. The recovery took millions of years, but it was relatively rapid compared to the extinction itself. Evolution filled ecological niches vacated by extinct species. Genetic variation increased as populations recovered from the bottleneck created by extinction. Diversity rebounded. This recovery suggests that while the Devonian extinction was severe, it was not so catastrophic as to permanently damage life's ability to diversify and adapt. The Devonian extinction and the proposed supernova contribution to it teaches us several important lessons about how cosmic influences affect evolution. First, cosmic influences don't typically cause extinctions themselves. Rather, they're one stressor among many.
A supernova alone might not have caused the Devonian extinction, but combined with climate change, ocean anoxia, and other stresses, it could have tipped the balance. Second, cosmic influences affect ecosystems unevenly. Shallow water organisms are affected more than deep water ones, surface-dwelling organisms more than underground dwellers, organisms dependent on zooxanthellae symbiotes more than independent organisms. The selective nature of the stress creates differential extinction and survival, which shapes evolution. Third, cosmic stress events create selection pressure. Organisms and lineages that survive cosmic stress events are those with enhanced radiation resistance, effective DNA repair, robust immune systems, or flexibility in diet and habitat. These traits become more common in post-extinction survivor populations. Fourth, extinction events create evolutionary opportunity. With much of the ecological landscape vacated by extinct species, surviving lineages can diversify, fill new niches, and evolve in new directions. The Devonian extinction was a crisis, but it was also an opening for new evolutionary possibilities. These lessons are critical as we now turn our attention to human evolution specifically. Our ancestors did not evolve in a vacuum. They evolved in a cosmos where supernovae occasionally exploded, where cosmic rays periodically increased, where Earth's protective shields periodically weakened. The emergence of humans, the evolution of our unique traits, occurred within this cosmic context. And just as the Devonian extinction demonstrates how cosmic influences can have profound effects on macroscopic evolutionary trajectories, similar influences were likely acting on the hominin lineage, smaller in scale perhaps, but accumulating over millions of years into significant evolutionary effects.
We've traveled through Earth's history, witnessed the Devonian extinction, and explored how cosmic influences can reshape life on a planetary scale. Now we arrive at the most crucial moment in our narrative, the emergence of hominins, our ancestors, a species that evolved during a period of elevated cosmic ray exposure, under conditions of environmental stress that may have been partly driven by cosmic influences. The hominin lineage emerged in Africa roughly 7 to 4 million years ago. This was a time of profound environmental change, a time when Africa's climate was becoming more unstable, when forests were declining and grasslands were expanding, when new ecological opportunities and challenges created selection pressure for new adaptations. But it was also a time when Earth's cosmic radiation environment was changing too. Our solar system was entering a region of the galaxy with elevated baseline cosmic ray flux, a galactic spiral arm passage that would last millions of years. Additionally, during this 10 million year window, several nearby supernovae may have occurred, temporarily spiking cosmic ray exposure even higher. This is the crucial context for understanding hominin evolution. Our ancestors did not evolve in a placid, stable environment. They evolved under pressure. Environmental pressure from climate change, pressure from competition with other species, and pressure from increased cosmic radiation. Let's set the scene. Between 7 and 4 million years ago, the African continent was undergoing dramatic environmental change. The climate was becoming cooler and drier, a trend that had been underway since the Miocene period, but was accelerating during this particular era. Tropical rainforests that had covered much of Africa were fragmenting into smaller patches, separated by expanding grasslands and savannas. This transformation created a mosaic of habitats, dense forests in some areas, open grasslands in others, intermediate zones with scattered trees and shrubs. For organisms adapted to forest life, this was a crisis. Their habitats were disappearing. But for organisms flexible enough to adapt to the new conditions, it was an opportunity. Among the primates living in Africa at this time were the australoid apes. These included the ancestors of modern gorillas, chimpanzees, and humans. These were all forest or forest edge dwellers, adapted to life in trees or in mixed forest grassland environments. As forests fragmented, populations of ancestral apes became isolated in different forest patches. Isolated populations diverged from each other, evolving different adaptations. Eventually, some populations diverged so much that they became distinct species. This is speciation through allopatry, geographic isolation causing divergence. One population, our direct ancestor, was isolated in African forest patches that were being fragmented by expanding grasslands. This population faced a choice: adapt to the shrinking forest habitat or adapt to the new grassland environment. Some ancestral apes adapted to grasslands. They're the ones who became hominins. The earliest recognized hominins are called australopithecines, from the genus Australopithecus, which means southern ape. The earliest specimens date to roughly 7 to 4.4 million years ago. The most famous australopithecine is Lucy, a specimen of Australopithecus afarensis that lived roughly 3.2 million years ago. What makes australopithecines distinctly hominin, what separates them from apes, is their bipedalism. They walked upright on two legs. Their fossil skeletons show multiple adaptations for upright walking: an upright spine, forward-facing foramen magnum, the hole where the spinal cord enters the skull, a pelvis oriented for bipedal locomotion, and hind limbs adapted for striding. But their brains were still relatively small, roughly 400 to 500 cubic centimeters, only slightly larger than modern ape brains, which are 400 to 600 cc, depending on species. Australopithecines were transitional between apes and later humans. They had acquired bipedalism, but they retained many ape-like features. They were successful, occupying African environments for millions of years, diversifying into several different species. Now, here's the crucial question: what drove the evolution of bipedalism in early hominins? Traditional explanations focus on terrestrial factors. Bipedalism might have been advantageous in open grassland environments, providing better vision to spot predators. Or it might have been advantageous for feeding, reaching high fruits or seeds. Or it might have been advantageous for thermoregulation, exposing less surface area to direct sun. These terrestrial explanations are plausible and probably correct. Bipedalism likely provided multiple advantages in grassland environments. But consider the cosmic context. Between roughly 7 and 4 million years ago, our solar system was entering or was positioned within a galactic spiral arm. During this period, baseline cosmic ray exposure at Earth's surface was elevated compared to periods in quieter galactic regions. Additionally, during this 10 million year window, several nearby supernovae may have occurred, temporarily spiking cosmic ray exposure even higher. During periods of elevated cosmic ray exposure, mutation rates increase. This is not a large effect, maybe a 20 to 50% increase in mutation rates during a galactic spiral arm passage, but over millions of generations it accumulates. Traits that arise from mutations become more common, and traits providing advantages are selected for by natural selection. This means that during the Australopithecine era, genetic variation in hominin populations was higher than it would have been during quieter cosmic times. Selection had more variation to work with. Advantageous traits like bipedalism could arise more frequently and become fixed in populations more rapidly.
But there's another angle to consider. Bipedalism comes with costs as well as benefits. Walking upright exposes the chest and abdomen to solar radiation. Bipedal animals have a more constrained pelvis, which creates difficulties in childbirth, especially as brain size increases. Bipedalism is energetically expensive.
Bipedal walking requires more energy than quadrupedal locomotion. Why would natural selection favor such a costly adaptation? In a normal environment, the costs might outweigh the benefits. But in an environment of elevated environmental stress, including elevated cosmic radiation, individuals with enhanced capacity to tolerate stress, enhanced immune function, enhanced DNA repair, or simply greater robustness might have additional advantage. Bipedalism, emerging from mutation and selected for by traditional environmental pressures, grassland habitat, feeding advantages, might have also been influenced by selection for overall robustness during periods of radiation stress. Individuals and lineages that acquired bipedalism also tended to acquire other adaptations for stress tolerance. These traits became linked evolutionarily. This is speculative, but it's plausible within the framework of evolutionary biology. Cosmic radiation, by elevating mutation rates and creating selection pressure for robustness, could have contributed to the evolutionary trajectory that produced bipedal hominins. While Australopithecines were still relatively small-brained, the stage was set for an extraordinary evolutionary development, rapid increase in brain size. Beginning roughly 2.8 million years ago, a new hominin genus emerged, Homo. Early Homo species, like Homo habilis, had larger brains than Australopithecines, around 650 cubic centimeters, a significant increase just over a few 100,000 years. This rapid increase in brain size would accelerate over the next several million years. Homo erectus, emerging roughly 1.9 million years ago, had a brain size of 800 to 1100 cubic centimeters. Homo neanderthalensis, evolving roughly 400,000 years ago, had a brain size of 1400 to 1700 cubic centimeters. Homo sapiens, our species, evolved with a brain size of 1200 to 1800 cubic centimeters. This rapid increase in brain size is the defining feature of human evolution. It's what makes us human, our large brains, our intelligence, our capacity for abstract thought. But what drove this rapid increase? And here's where cosmic rays become particularly relevant. Brain development is energetically expensive and metabolically demanding. But brain tissue is also particularly vulnerable to radiation damage. DNA in neurons is being replicated during brain development, and any radiation damage during this critical period could affect neural development. Yet paradoxically, brain cells also have some of the most robust DNA repair mechanisms in the body. They've had to evolve enhanced DNA repair because of the vulnerability of developing neural tissue to damage. Could enhanced cosmic ray exposure during the emergence of the Homo genus have selected for individuals with enhanced neural development capacity and enhanced DNA repair in brain tissue? Could this have contributed to the rapid evolution of larger brains? Here's a deeper principle of evolutionary biology. Organisms face trade-offs between different traits. Energy invested in DNA repair mechanisms is energy not available for other functions. Growth is slowed, reproduction is delayed, lifespan might be reduced. But in environments of high radiation stress, such trade-offs become favorable. An organism investing in enhanced DNA repair survives better, reproduces successfully despite the energy cost, and passes on the genes for enhanced DNA repair to its offspring. Over millions of years, this selection can produce populations with significantly enhanced DNA repair capabilities. But here's the interesting part. Enhanced DNA repair mechanisms often have side effects. They can be associated with enhanced immune function, enhanced metabolic efficiency, enhanced cognitive function, because many of the same cellular mechanisms involved in DNA repair are involved in other cellular processes. During periods of elevated cosmic ray exposure, such as the millions of years when hominins were evolving, selection for enhanced radiation resistance would have selected for enhanced DNA repair, which would have had multiple physiological and neurological consequences. One of those consequences might have been enhanced capacity for brain development and cognitive function, not directly selected for, but a side effect of selection for radiation resistance. To be clear, cosmic rays were not the only environmental stress that hominins faced. Climate change was profound during this period. Habitat fragmentation created ecological pressure. Predation was a threat. Competition with other species and with other hominin populations was intense. Cosmic radiation was one stress among many, but here's the crucial point. Cosmic radiation stress was relentless. It occurred every day, every generation, for millions of years. Unlike climate fluctuations, which can be extreme but are temporary, or predation events, which are episodic, cosmic radiation was constant. Constant selection pressure, if it's selecting for broadly beneficial traits like robust DNA repair and physiological stress resistance, can accumulate into significant evolutionary effects over millions of years. So, did cosmic rays cause hominin evolution? The answer is nuanced. Cosmic rays did not directly cause the emergence of bipedalism or the increase in brain size. These traits were selected for because they provided advantages in terrestrial environments, grassland habitats, feeding opportunities, furrow regulation, intelligence, and tool-making. But cosmic rays contributed to the conditions under which these traits evolved. By elevating mutation rates during galactic spiral arm passages, cosmic rays increased genetic variation. By creating selection pressure for enhanced stress resistance and DNA repair, cosmic rays favored populations with these traits. By these indirect mechanisms, cosmic rays may have accelerated human evolution, made it more likely that beneficial mutations would arise and spread, created conditions favorable for rapid evolutionary change. Our ancestors did not evolve in spite of cosmic radiation. They evolved within a cosmic radiation environment, and that environment shaped them. We carry in our bodies and brains the mark of billions of years of exposure to cosmic rays, of selection for radiation resistance, of evolution under cosmic pressure. We are quite literally shaped by the cosmos.
We've arrived at the heart of our narrative, the evolution of the human brain. This is where cosmic influences potentially become most profound, most specific, most directly relevant to who we are. For it is the human brain, its size, its structure, its remarkable capacity for abstract thought, language, imagination, and self-awareness that makes us distinctly human. The evolution of our brain is one of the fastest evolutionary changes in the history of life. In just 3 million years, brain size roughly tripled. This is extraordinarily rapid on evolutionary timescales. To understand how cosmic rays might have influenced this dramatic change, we need to examine the genetics of brain development, the selection pressures involved, and the precise period during which this change occurred. Brain development is controlled by hundreds of genes, but a few have particularly large effects. One of the most important is the ASPM gene, abnormal spindle-like microcephaly-associated protein, located on chromosome 1. This gene encodes a protein crucial for regulating the number of cell divisions in neural progenitor cells during brain development. In chimpanzees, ASPM has a specific DNA sequence. In humans, ASPM has a different sequence. This difference is the result of mutations that accumulated during human evolution. These mutations alter the protein's function in ways that enhance the proliferation of neural progenitor cells, leading to more neurons being produced and larger brains developing.
Crucially, these ASPM mutations arose relatively recently in evolutionary time, most of them within the past 200,000 to 5 million years, with one particularly important mutation cluster occurring within the past 37,000 years. This means that significant changes to ASPM accumulated very rapidly, much faster than expected based on typical mutation rates and selection speeds. How could such rapid evolution of a critical brain development gene occur? The answer involves both natural selection, brain size provided advantages in the African environment, and increased mutational input, mutations being produced, giving selection more variation to work with. Here where cosmic rays become central. Mutations affecting ASPM and other brain development genes arise in germline cells, sperm and egg precursor cells. The DNA in these cells is being replicated during the reproductive years, and each replication is an opportunity for mutation. Cosmic rays ionize cells throughout the body, including germline cells. When cosmic ray particles pass through the nuclei of sperm-producing cells or egg-producing cells, they create DNA damage. Some of this damage is accurately repaired, but some results in mutations, permanent changes to the DNA sequence that will be inherited by offspring. During periods of elevated cosmic ray exposure, such as the period from roughly 7 to 3 million years ago, when our solar system was entering or was positioned within a spiral arm of the galaxy, germline mutation rates would have been correspondingly elevated. A 50% increase in cosmic ray exposure would result in roughly a 50% increase in mutation rate. This might seem modest, but over millions of generations, it compounds dramatically. If a beneficial mutation arises once per million births in normal times, it might arise 1.5 times per million births during high cosmic ray periods. Over a million generations, this represents a substantial increase in the frequency of beneficial mutations appearing. For genes like ASPM, where mutations can enhance brain size and cognitive function, this increased mutational input means that beneficial variations would arise more frequently. Natural selection would then act on this increased variation, spreading beneficial mutations through populations more rapidly. Another gene crucial for human uniqueness is FOPX2, forkhead box protein P2, located on chromosome 7. This gene is involved in language development and has been called the language gene, though this oversimplifies its function. FOPX2 is involved in brain development, vocal learning, and coordination of speech and hearing. In humans, FOPX2 has 2 amino acid differences compared to chimpanzees. These differences arose during human evolution, with fossil and genetic evidence suggesting they became fixed roughly 200,000 to 600,000 years ago. The FOPX2 mutations are particularly interesting because they appear to have arisen rapidly, in evolutionary terms, and then were strongly selected for. The fact that they became fixed, reaching 100% frequency in the human population, suggests they provided a significant advantage. During the period when FOPX2 mutations were arising and being selected for, cosmic rays were still elevated compared to modern times. We're only recently exiting the spiral arm passage that began millions of years ago. This elevated cosmic ray exposure meant that mutations in FOPX2 were arising more frequently than they would in a low cosmic ray environment. This phenomenon, rapid evolution driven by increased mutation rates during periods of elevated environmental stress, has precedent in evolutionary history. During the Cambrian explosion, roughly 540 million years ago, animal body plans diversified explosively over a relatively short period. Evolutionarily speaking, it was still millions of years. Multiple lines of evidence suggest that cosmic radiation may have contributed to this explosion of diversity. During the Cambrian, Earth's magnetic field was undergoing frequent reversals, and the solar system may have been in a region of the galaxy with elevated cosmic ray background. The combination meant higher mutation rates, more genetic variation, and faster evolution. The lesson is that periods of elevated cosmic ray exposure are also periods when evolution can accelerate. Genes can change more rapidly, new traits can emerge and become fixed in populations more quickly. The Cambrian explosion demonstrates this principle on a large scale. Human brain evolution demonstrates it on a more focused scale. But increased mutation rates alone don't explain the evolution of human intelligence. Mutations are random, most are neutral or harmful. For beneficial cognitive mutations to become fixed, natural selection had to be actively favoring intelligence. What selection pressures in the African environment would favor enhanced cognition? Several factors. Tool use and manufacture. Homo species, our ancestors, increasingly relied on tools. Making increasingly sophisticated tools required problem-solving ability and manual dexterity. Individuals with enhanced spatial reasoning, enhanced memory, enhanced ability to plan and execute complex tasks would be better at making tools and surviving with them. Social complexity. Hominin societies became increasingly complex. Larger group sizes, cooperation, formation of alliances, development of social hierarchies, all these require sophisticated social cognition. Individuals with enhanced theory of mind, ability to understand others' mental states, enhanced language ability, enhanced social reasoning would have advantages in navigating complex social environments. Teaching and cumulative culture. Humans began to develop cumulative culture, knowledge and techniques passed from generation to generation, building on previous knowledge. This requires teaching ability and learning ability. Individuals with enhanced cognitive capacity to learn from others, to teach others, to understand abstract concepts would be favored. Novelty and adaptation. The African environment during hominin evolution was unstable, climate fluctuating, habitats changing, new species appearing. Adaptability, the ability to solve novel problems, to develop new strategies, to be cognitively flexible, would be advantageous. All of these selection pressures favored enhanced cognition. Natural selection was actively selecting for intelligence. The question is, how rapidly did this selection act?
In a normal environment with normal mutation rates, beneficial mutations in brain development genes might be relatively rare. But during periods of elevated cosmic ray exposure, with mutation rates elevated by 20%, 50% or more, beneficial mutations would arise more frequently. Natural selection could work faster, spreading beneficial mutations through populations more efficiently. Let's trace the timeline. 7 to 4 million years ago, our solar system enters or is within a galactic spiral arm. Baseline cosmic ray exposure increases. Early hominins emerge, acquiring bipedalism. Mutation rates are elevated. Genetic variation in early hominin populations is enhanced. 3 million years ago, Homo genus emerges. Brain size begins to increase noticeably. Mutation rates remain elevated due to continued galactic spiral arm passage. Selection for enhanced cognition from emerging social and tool use pressures begins to accelerate brain size evolution. 2 million years ago, Homo erectus emerges with significantly larger brains, 950 cc. Tool sophistication increases dramatically. Fire is discovered and controlled. Migration out of Africa begins. Cosmic ray exposure remains elevated. 800,000 to 200,000 years ago, brain size increases further. Homo neanderthalensis and archaic Homo sapiens emerge with even larger brains. Language, art, and symbolic thinking emerge. Cosmic ray exposure remains elevated, though our solar system is gradually exiting the spiral arm. 200,000 years to present, Homo sapiens achieves modern form, with brain size reaching 1,400 cc on average. Language becomes fully developed. Abstract thought, art, religion, philosophy, science all emerge. Cosmic ray exposure is declining as we exit the galactic spiral arm, returning toward baseline. This timeline is striking. The period of maximum brain size evolution, roughly 3 to 1 million years ago, coincides with peak galactic spiral arm passage. The period of emergence of fully modern human cognition and symbolic thought, roughly 200,000 to 70,000 years ago, coincides with the tail end of the spiral arm passage. Is this timing coincidental? It's impossible to say definitively, but the correlation is suggestive. Here's another angle to consider. Brain development is not only controlled by genes, it's constrained by physical and metabolic limits. The human head can only get so large before childbirth becomes physically impossible. The brain can only consume so much energy before metabolic demands exceed what the body can provide. These constraints mean that brain size evolution is limited by the availability of genetic variation. If mutations in brain size genes are rare, then brain size evolution is slow. But if mutations are more abundant, then more variation is available, and selection can work faster within the constraints. During periods of elevated cosmic ray exposure, more genetic variation becomes available. Selection can fine-tune brain size genes within the physical and metabolic constraints. Brain size can increase more rapidly. When cosmic ray exposure returns to normal, mutational input decreases, variation becomes scarce, and evolution slows. This matches what we observe: rapid brain size evolution during the period of elevated cosmic ray exposure, slower evolution after. The integration of cosmic and terrestrial selection pressures. The most important point is that cosmic radiation didn't act alone. Cosmic radiation provided the variation, the mutations that natural selection could work with. But natural selection, driven by competition, predation, social complexity, technological innovation, environmental change, determined which mutations became fixed and which remained rare. Cosmic rays and terrestrial selection pressures acted together. A mutation that enhanced brain development might have arisen through cosmic ray-induced mutagenesis, but it would only spread through the population if it provided an advantage in the African environment. The cosmic contribution was providing more opportunities for beneficial mutations to arise. The ecological and social pressures were selecting for intelligence. This integrated view, cosmic and terrestrial factors working together, is the most complete and scientifically grounded understanding of how cosmic rays might have influenced human evolution. We have arrived at a profound realization. Human consciousness, human intelligence, human capacity for abstract thought and self-reflection, these defining features of humanity may have been influenced, shaped, and perhaps accelerated by cosmic radiation.
The electromagnetic forces that bind atoms into molecules, the gravity that holds planets in orbit, the nuclear fusion that powers stars, the death throes of massive stars creating supernovae and cosmic rays, all of these cosmic processes, playing out across billions of years and distances almost incomprehensible to human understanding, may have contributed to the emergence of minds capable of understanding the cosmos itself. We are not separate from the cosmos. We are part of it. Our intelligence emerged from cosmic influences. Our capacity to contemplate the stars, to detect cosmic rays, to measure radiation, to propose theories about how the cosmos works, this capacity itself may trace back to cosmic influences on our evolutionary history. This is the deepest meaning of the hypothesis we've explored throughout this narrative. Humans are shaped by the cosmos, not just materially, but cognitively, evolutionarily, fundamentally.
We've explored how cosmic rays may have accelerated the evolution of human intelligence through their effects on mutation rates and genetic variation. But there's another defining characteristic of humanity that emerged earlier in our evolutionary story: bipedalism. Our ancestors stood upright. They walked on 2 legs instead of 4. This simple anatomical change, revolutionary in its implications, was one of the first steps on the path to becoming human. Bipedalism seems obvious to us. We don't think twice about walking upright. It's so fundamental to human experience that we rarely contemplate how unusual it actually is. Among all the primates, apes, monkeys, lemurs, and other members of our order, humans are the only ones that habitually walk upright. Even our closest living relatives, chimpanzees and bonobos, are knuckle walkers, moving on 4 limbs with their knuckles bearing their weight. Why did our ancestors make this switch? What advantages does bipedalism provide that would outweigh its considerable costs? And how might cosmic radiation have influenced this evolutionary transition? Before we explore the advantages, we need to understand what bipedalism costs us. Walking upright is actually less efficient than quadrupedal locomotion. When you walk on 4 limbs, as mammals typically do, your body's center of mass barely moves up and down with each step. The limbs act like pendulums, and the energy used to move one limb is partially recovered when that limb swings back. It's efficient. When you walk upright on 2 legs, your center of mass rises and falls with each step. You're essentially doing a series of tiny hops, lifting and lowering your entire body weight with each stride. This requires more energy. Studies comparing bipedalism versus quadrupedal locomotion show that bipedalism requires about 50% more energy for the same distance traveled. A bipedal animal has to eat more to maintain the same level of activity. Additionally, bipedalism creates a narrower base of support. A quadrupedal animal with 4 widely spaced limbs is stable and can move quickly. A bipedal animal balancing on 2 legs is less stable and must be more careful about balance and footfalls. This makes bipedal animals potentially more vulnerable to falling, more vulnerable to attack from predators that can knock them off balance. And bipedalism changes pelvic anatomy in ways that create reproductive consequences. The bipedal pelvis is narrower than the quadrupedal pelvis to allow for efficient upright walking. But a narrower pelvis means a smaller birth canal. Human babies have larger brains than ape babies, making childbirth already difficult. The narrow bipedal pelvis makes it even more difficult. Childbirth in humans is extraordinarily dangerous for both mother and infant compared to childbirth in other primates.
So bipedalism comes with significant costs: higher energy consumption, reduced stability, increased danger during reproduction. For such a costly adaptation to evolve, the advantages must be substantial. Paleontologists and evolutionary biologists have proposed several advantages that bipedalism might have provided in the African environment where early hominins lived. The savanna hypothesis: as African forests fragmented and grasslands expanded, bipedalism would provide better visibility. Standing on two legs allows you to see farther above the grass, helping you spot predators or prey. For creatures transitioning to grassland habitats, this visibility advantage might outweigh the energetic costs. The feeding hypothesis: bipedalism frees the arms and hands. In grassland and forest edge environments, trees might be scattered and distant. Being able to walk upright while carrying food, carrying tools, or carrying infants would be advantageous. Your hands are no longer committed to locomotion; they're available for other tasks. The thermoregulation hypothesis: standing upright exposes less surface area to direct sunlight. In open grassland environments with intense sun, being able to reduce sun exposure during the hottest parts of the day could provide a thermoregulatory advantage. The display hypothesis: standing upright is visually impressive. It might serve a social function, intimidating rivals, attracting mates, signaling status in group hierarchies. If social status correlates with reproductive success, then traits that signal status, like impressive upright posture, could be selected for. All of these hypotheses have merit. Bipedalism probably arose because multiple advantages combined to outweigh the costs. But the question we need to ask is under what circumstances would such a costly adaptation be selected for? What would tip the balance in favor of bipedalism despite its substantial drawbacks? Here's a principle from evolutionary biology. Adaptations to costly traits are more likely to be fixed when organisms are under environmental stress. When survival margins are tight, when energy is scarce, when predation pressure is intense, organisms are under strong selection pressure. In these environments, adaptations that provide any advantage, even small advantages, can spread through populations. During the period when early hominins were evolving bipedalism, roughly 7 to 4 million years ago, Africa was experiencing profound environmental stress. Climate was becoming colder and drier, forests were fragmenting, food sources were becoming less abundant and more scattered. Predation pressure may have increased as new predators appeared. In this environment of stress, an adaptation like bipedalism, despite its costs, might provide enough advantage to be selected for. The visibility advantage in grassland environments, the ability to carry food and infants, the thermoregulatory advantage, each might be small, but together they could provide enough advantage.
And here's where cosmic radiation enters the picture. We've established that during this period, roughly 7 to 4 million years ago, Earth was experiencing elevated cosmic ray exposure due to galactic spiral arm passage. This cosmic radiation added another layer of environmental stress to the already stressful conditions caused by climate change and habitat fragmentation. Cosmic ray exposure causes mutation and increases disease rates through its mutagenic effects. It creates oxidative stress in cells through free radical production. It affects immune function. For organisms living under this radiation stress, selection would favor traits that enhance stress tolerance, enhanced DNA repair, enhanced immunity. Organisms with robust physiological stress responses, enhanced antioxidant production, enhanced inflammation control, enhanced immune function would survive better under elevated radiation exposure than organisms without these traits. And here's the crucial connection.
Many of these same physiological traits that enhance radiation resistance also enhance the capacity to tolerate other forms of stress: metabolic stress, thermal stress, predation stress. So during a period when hominins were under stress from climate change, habitat fragmentation, and cosmic radiation, selection would favor individuals with enhanced stress tolerance. This selection pressure would act on multiple traits simultaneously, not just radiation resistance, but overall robustness and adaptability. Bipedalism, emerging as an adaptation to terrestrial environments, would be more likely to become fixed in populations that already had enhanced stress tolerance. Bipedal individuals who also possessed enhanced DNA repair, enhanced immunity, and enhanced metabolic flexibility would survive better than bipedal individuals without these traits, or than quadrupedal individuals lacking stress tolerance. The interaction of cosmic and terrestrial selection. This is the key insight. Cosmic radiation didn't directly cause bipedalism, but it created environmental conditions, enhanced stress tolerance, enhanced immunity, enhanced adaptability that made bipedalism more viable as an evolutionary strategy. Bipedalism was selected for because of terrestrial advantages, visibility, feeding efficiency, thermoregulation. But it became fixed in populations faster, spread to higher frequencies, and became established more reliably because the same cosmic and terrestrial stresses that selected for radiation resistance also selected for the overall robustness and adaptability that allowed bipedal creatures to survive despite the costs of bipedalism. This is how cosmic and terrestrial factors interact. They don't work independently, they work synergistically. Each enhances the conditions for the other. Terrestrial environmental change created selective pressure for bipedalism. Cosmic radiation created selective pressure for stress tolerance and adaptability. These pressures acted on the same populations simultaneously, reinforcing each other, accelerating the overall trajectory of hominin evolution. One final piece of this puzzle. Bipedalism's energetic costs would be prohibitive unless hominins found ways to increase their energy intake. How did early hominins compensate for the 50% energy penalty of bipedal locomotion? The answer involves dietary changes. Early hominins began eating meat. Homo species are carnivorous, or more precisely, omnivorous with a significant meat component. Meat is energy-dense food. It provides more calories per unit mass than plants, and it requires less processing, digestive effort to extract those calories. By incorporating meat into their diet, early hominins could meet the increased energy demands of bipedal locomotion. But hunting requires tools, skill, cooperation, and intelligence. It creates selective pressure for enhanced cognitive abilities. And here's where the cosmic connection becomes even more intricate. During periods of elevated cosmic ray exposure, when mutation rates are elevated and genetic variation is abundant, selection for enhanced hunting ability and intelligence would occur more rapidly. The mutations underlying enhanced hunting ability and intelligence would arise more frequently, be selected more efficiently, and spread through populations more quickly. So cosmic rays didn't just make bipedalism possible by enhancing stress tolerance, they indirectly promoted the cognitive and behavioral innovations, hunting, meat eating, tool use that made bipedalism energetically feasible. Bipedalism represents a crucial choice point in hominin evolution. Once early hominins committed to upright walking, a cascade of evolutionary consequences was set in motion. Bipedalism freed the hands, enabling tool use. Tool use required enhanced cognition. Enhanced cognition enabled hunting, cooperation, social complexity, and eventually language, culture, and civilization. If bipedalism hadn't evolved, none of this would have followed. We would not be here. Our entire species, our entire lineage traces back to that fundamental adaptation, standing upright. And that adaptation, while primarily driven by terrestrial environmental pressures, may have been facilitated, made more likely, made more rapid, made more successful by cosmic radiation. By creating conditions that selected for stress tolerance and adaptability, cosmic rays provided the physiological foundation on which bipedalism could be built and maintained. There's a profound irony and beauty to this realization. The very radiation that can damage DNA, cause cancer, and create mutations that are harmful also created the conditions that led to human evolution. Cosmic rays are simultaneously a threat and an opportunity, a danger and a catalyst. Our ancestors stood upright in the cosmic rain. Quite literally, cosmic rays were passing through them every moment, and that experience, accumulated over millions of generations, shaped their physiology, their behavior, their evolutionary trajectory. We are creatures of cosmic stress and adaptation. Our upright posture, our freed hands, our enhanced cognition all trace back to an environment where multiple stresses, climate change, habitat fragmentation, and cosmic radiation pressed upon our ancestors and selected for those who could survive and adapt. We literally stand in the shadow of cosmic influences. Our very stance, our very nature is a product of standing upright in the cosmic rain.
We've journeyed far in this narrative, from the scale of the galaxy down to the molecular scale, from the deaths of distant stars to the emergence of human consciousness. We've traced how cosmic rays, those tiny particles streaming across the void, have woven themselves into the very fabric of life on Earth, and specifically into the emergence of our species. Now, as we reach the end of our exploration, we need to step back and contemplate what this all means. What are the implications of understanding that human evolution has been shaped by cosmic influences? What does it tell us about ourselves, about life, about our place in the universe? The first insight is one of profound continuity. Cosmic rays did not simply influence human evolution, they've been shaping life since the very beginning. We traced how cosmic radiation may have driven synthesis of prebiotic organic molecules, how it influenced the chirality of life's building blocks, how it powered the chemistry of the RNA world. For 4 billion years, life has existed in a cosmos where radiation from distant stars continuously rains down, continuously influencing evolution through mutation and selection pressure. We are not separated from the cosmos by any fundamental boundary. We are embedded in it. We are made of stardust. The atoms in our bodies were forged in stellar interiors and distributed across the galaxy by supernovae. And we are shaped by stardust. The radiation from those same stars has influenced the evolution of those atoms into living, conscious beings. This means that every feature of humanity, our bipedal posture, our large brains, our capacity for language and abstract thought, our ability to contemplate the cosmos itself, carries the mark of cosmic history. We are not just physically composed of material from the stars, we are evolutionarily composed of cosmic influences. A second insight concerns the probabilistic nature of evolution itself. Evolution is not a directed process marching toward predetermined goals. It's a process of random mutation filtered by natural selection. But randomness has structure when viewed over long timescales. Over millions of years and millions of organisms, random mutations create patterns. Selection acting on those mutations creates trends. Cosmic rays increase the rate of randomness. They increase mutation rates. During periods of elevated cosmic ray exposure, evolution becomes more random in a sense. More mutations occur. More genetic variation is produced.
But this increased randomness is actually filtered through selection more efficiently. Beneficial mutations arise more frequently, selection finds them faster, advantageous traits spread more quickly. This suggests that cosmic influences don't determine evolution. They don't specify that bipedalism must emerge or that intelligence must increase. Rather, cosmic influences bias the probabilities. They make certain evolutionary outcomes more likely. In a low cosmic ray environment, human intelligence might never have evolved. In a high cosmic ray environment, the conditions are more favorable for rapid evolution of enhanced cognition. Our existence as conscious beings capable of understanding the cosmos is not inevitable. It's contingent, dependent on the particular cosmic history we happen to experience. In a different galaxy, around a different star, in a region with different supernovae frequencies and a different magnetic field history, life might have evolved very differently, or not at all. We've emphasized throughout this narrative that cosmic radiation is both a danger and an opportunity. It's a curse. It damages DNA, increases cancer rates, causes genetic diseases. It's a gift. It creates variation, accelerates evolution, provides the raw material for adaptation and innovation. This duality reflects a deeper principle. Evolutionary progress is not separate from risk. Evolution works through variation and selection. Variation comes partly from cosmic rays, from the mutations they induce. These mutations are mostly neutral or harmful, but occasionally beneficial. The beneficial mutations wouldn't arise without the cosmic radiation inducing them. Progress is inseparable from the danger that creates it. This has implications for how we understand our own nature. We are the product of cosmic radiation. Our intelligence, our consciousness, our very capacity to understand and appreciate the cosmos all arose partly through the mutagenic effects of cosmic rays. We literally owe our existence to radiation that could kill us. This is humbling. It suggests that there's no way to have the benefits of cosmic influence without the risks. We couldn't have intelligence without the increased mutation rates that cosmic rays enable. We couldn't have evolution toward greater complexity and adaptability without the genetic damage that radiation causes. The gift and the curse are inseparable. So far, we've focused on prehistoric cosmic influences, how cosmic rays shaped human evolution over millions of years. But cosmic influences continued after humans emerged. They're still active today. During recorded human history, we've experienced at least one grand solar minimum, the Maunder minimum from 1645 to 1715. During that period, cosmic ray flux at Earth increased. Whether this had any effect on human biology, human development, or human history is difficult to establish definitively, but it's a reminder that cosmic influences are ongoing. More speculatively, one could ask whether periods of elevated cosmic radiation in the past might have influenced human history, whether they caused disease patterns, whether they contributed to periods of social disruption, whether they influenced technological innovation. The evidence for such effects is weak, but the principle is plausible. More intriguingly, one could wonder whether the particular distribution of nearby supernovae in historical times influenced human civilizations. If a nearby supernova flooded Earth with cosmic rays, causing disease and crop failures, it could have triggered social upheaval, migration, the rise or fall of civilizations. Such effects would be impossible to trace definitively, but they illustrate that cosmic influences on humans didn't end when we became human. They continued, though on different timescales and with different mechanisms than evolutionary influence. What about the future? How will cosmic influences shape humanity going forward? Our solar system is gradually exiting the galactic spiral arm that has been our home for millions of years.
As we exit, cosmic ray exposure is declining toward baseline levels. Within the next few million years, we'll be in a quieter region of the galaxy. The elevated mutation rates that characterized the period of human emergence will return to lower baseline levels. From an evolutionary perspective, this means that the conditions that favored rapid evolution during human emergence are ending. Future evolution, if it occurs, will do so with lower mutation rates and less genetic variation. This could slow human evolution, though modern humans have largely stepped outside of natural selection through technology and medicine, so evolutionary change may be minimal anyway. But from a cosmic perspective, there's another consideration. We're not passive victims of cosmic radiation. We are becoming active participants. Through space exploration, through our increasing understanding of physics and astronomy, through our development of technology, we are beginning to interact with the cosmos actively, rather than just being shaped by it passively. Humanity is developing the capacity to detect cosmic rays, to measure radiation, to understand the physics of supernovae and galactic cosmic rays. We're beginning to shield spacecraft and astronauts from cosmic radiation. We're even beginning to contemplate becoming a multiplanetary species, expanding beyond Earth. This represents a fundamental shift in humanity's relationship with cosmic influences.
For billions of years, life was simply subject to cosmic radiation. For millions of years, human evolution was shaped by it. But now, for the first time, a species, us, is becoming aware of cosmic influences and potentially capable of controlling them. This awareness brings responsibility. Understanding that we've been shaped by cosmic influences could lead to a sense of humility, recognizing our contingency, our dependence on cosmic history, our place within a larger cosmos. But it could also lead to a sense of awe and gratitude. We exist because of cosmic processes. Our consciousness, our intelligence, our capacity to love, to create, to contemplate, all of these emerged from the universe. We are, in a very real sense, the universe becoming aware of itself. With this understanding comes the responsibility to use our emerging powers wisely. As we become capable of controlling our own evolution through genetic technology, we should remember that the variations we inherit came from cosmic radiation. The genetic diversity we possess is a gift from the cosmos. We should be cautious about eliminating that diversity in the pursuit of perfection. As we expand into space, we should remember that cosmic radiation is a threat to human health and survival. We'll need to develop shielding, to understand radiation biology, to evolve our strategies for surviving beyond Earth's protective magnetosphere. But we should also remember that we evolved under cosmic radiation. Some of our physiological adaptations, our DNA repair mechanisms, our stress tolerance, these are responses to cosmic radiation honed over millions of years. In space, away from Earth's protective shields, we'll need to rely on these cosmic radiation-honed adaptations. This narrative suggests a new perspective on human nature itself. We often think of humans as separate from nature, as transcending biology through our intelligence and culture. But this narrative suggests something different. We are biological creatures thoroughly embedded in the natural world, shaped by ecological pressures, climate fluctuations, predation, disease, and cosmic radiation. Our intelligence isn't a transcendence of biology, it's a product of biology, shaped by cosmic history. Our consciousness isn't separate from nature, it's an emergent property of nature, arising through billions of years of evolution, shaped by cosmic influences. Our culture, our technology, our science, these are extensions of natural processes, not alternatives to them. This doesn't diminish human achievement or human consciousness. If anything, it elevates them. That consciousness could arise from the interaction of cosmic processes and terrestrial evolution makes consciousness more wondrous, not less. That we can understand the cosmos, that we can detect cosmic rays, measure radiation, understand the physics of supernovae, this is miraculous precisely because the cosmos produced conscious creatures capable of understanding itself. At the deepest level, this narrative is about synthesis, the synthesis of cosmic and biological scales, of physical processes and evolutionary processes, of past and future. Cosmic rays connect the scale of the galaxy to the scale of individual molecules. Supernovae connect the death of stars to the emergence of life. Evolution connects random mutation to the emergence of consciousness. Nothing in the universe stands alone. Everything is connected to everything else. The death of a star 10,000 light-years away influences mutations in human germline cells. Mutations in our ancestors, induced by cosmic rays, resulted in the emergence of consciousness capable of contemplating the cosmos. We stand now at a threshold in human history. For the first time, we're becoming aware of our cosmic origins. For the first time, we possess the knowledge and the technology to potentially influence our own evolution and to extend our existence beyond our home planet. For the first time, we can contemplate the cosmos that shaped us and understand, at least partially, how that shaping occurred. This is the gift that cosmic rays have brought us. Not just the ability to exist, but the ability to understand our own existence. Not just consciousness, but consciousness capable of appreciating life's profound place in the universe. Our ancestors stood upright in the cosmic rain, exposed to radiation from distant stars, yet from that exposure came the evolutionary innovations that led to us. We stand now at the threshold of space, looking outward towards the cosmos that shaped us, equipped with knowledge and tools our ancestors could never have imagined. We are cosmic creatures in the fullest sense, made of stardust, shaped by cosmic radiation, capable of understanding cosmic processes. The universe evolved consciousness, and that consciousness is now capable of reflecting on the universe that created it. This is the deepest meaning of the cosmic ray hypothesis of human evolution. We are not observers of the cosmos, separate from it. We are part of it. We're expressions of it. Our evolution is the universe's way of creating creatures capable of understanding itself. As we move forward, as our species develops, as we expand into space, as we continue to evolve culturally, if not biologically, we carry with us the mark of the cosmos. Our large brains, our upright posture, our complex language and abstract thought, our capacity for science and self-reflection, all bear the imprint of billions of years of cosmic influence. We are the universe becoming conscious of itself, and with that consciousness comes the responsibility to steward our cosmic heritage wisely, to use our intelligence to understand our origins and our place in the cosmos, and to ensure that life, this precious phenomenon that has arisen from cosmic processes, continues to flourish. The cosmic rays that shaped us continue to rain down, continue to influence evolution, continue to shape life on Earth and wherever else in the cosmos life has emerged. We are part of an ongoing cosmic process, a process that connects the births and deaths of stars to the emergence of consciousness, to the future of life itself. This is the ultimate gift of the cosmos. Not just existence, but awareness of existence. Not just life, but consciousness capable of appreciating life's profound place in the universe.